So let's start this afternoon session, afternoon at least for the people in Europe. The people in Japan is night session. And yeah, so the first speaker of this section is Irina Aref'eva. I really hope I didn't pronounce that too badly.
Oh, yes,
and,
you pronounce absolutely correct, yes.
Okay, that's great. And she's going to talk about black hole explosions. And yes, please start as soon as you're ready.
It is my big pleasure to give a talk at this interesting meeting. First of all, I would like to thank organizer for kind invitation. And as Filippo already said, I will speak about black hole explosions. Let me try, okay, like this. Let me first say that this presentation is based on 3 papers. Just a moment. Я не могу сейчас, у меня доклад. This talk was based on 3 papers, which I wrote in collaboration with Igor Varovich and Timofey Rusalov, and the overview of my talk will be the following. First, I will explain what means the problem of black hole explosions. Then I will present the scenario, how we proposed to solve this black hole explosion. I can say you the answer in few words. We just put some special constraints on the black hole parameters. So if there are special constraints, then there is no problem with black hole explosion. I will explain this scenario mainly for Reissner-Nordstrom black hole. So I will describe you how looks Reissner-Nordstrom black hole under constraints. And in this case, I will show that we can reproduce the page curve. And also, it is possible to solve this problem for different black hole, for example, for Kern-Newman black hole, as well as Reissner-Nordstrom and Kern-Newman, DS and ADS black hole. But because the time is limited, I will not tell much about these cases, but a session marked by this star. So I will not report it about these materials, but I will present the necessary material on backup slides. Of course, these materials are also presented in the paper which the reference on which I already mentioned. Okay, then I will also discuss the connection between explosion and information loss problem. Then I will pay special attention the influence of ions on all this consideration, and of course in the end I will go to conclusion. Okay, let me first explain the problem itself. In 1974, Stephen Hawking published the paper with the same title. In fact, I use his title for my talk today. So the title of his paper published in Nature is Black Hole Explosions. And the idea, and the main idea of his consideration is very simple. Of course, we know that the Schwarzschild black hole produce radiation like black bodies with temperature, so-called Fermi-Hawking temperature. And for example, for Schwarzschild black hole with temperature is equal to 1/8 pi m, where m is the mass of black hole. So during the process of evaporation, the mass of black hole is decreased, and the temperature is increased. It's absolutely evident from this formula. So in the end of evaporation, the temperature should be equal to infinity. Of course, there is open problem, better to say open question, whether this process continues, the process of evaporation continue until the entire mass of black hole has been converted to radiation, or whether it stops, then the temperature is close to the Planck temperature, or mass of black hole is close to Planck mass. Okay, but let's just ignore questions about Planck scales, and just suppose that we consider the evaporation till the end of the process. In this case, we end up with infinite energy, because according to Stefan Boltzmann law, the energy density of black body of radiation is given by this formula. So it is absolutely evident that zero temperature corresponds to infinite energy. And it is also clear that this is unphysical situation. This explosion problem is also very closely related with information loss problem, mentioned Hawking already in 1976, because the radiation entropy diverge at small m as m in power minus 3. So also the entropy in the end of evaporation become infinite. Of course, we can use the alternative approach and say just, okay, we have not go to the zero mass, we have stopped evaporation on the Planck scale. And this is a scene for quantum gravity effect. We don't know a real quantum gravity theory, so blah, blah, blah. Okay, so in other words, evaporation is not complete, we have to stop and no problem at all. However, I would like to say that, I would like to mention that Hawking and Page considered themselves the complete evaporation process, and I will try to do the same also today. So our main question is the following. Is it possible to describe the process of complete evaporation of black hole in framework of classical geometry and get a reasonable, reasonable results? Okay. And let me, as I already mentioned, our main result. The main result is that we can propose a scenario that in which we can avoid black hole explosion. And the main idea is the following. We use a special equation of state. That is a special relation between mass and other parameters. And if we use a very special relation between this parameter, in this case, we can avoid the problem of infinite temperature and infinite entropy in the end of evaporation, and the m goes to 0. Very important that we can solve this problem in the case that there are several parameters, at least 2, mass and some other. So from this, it is clear that I have nothing to offer in the Schwarzschild case. It's true. it's true that I can solve a problem, I can propose some scenario only in the case that there are some extra parameter. For example, cosmological parameter is also enough for me. So I cannot solve a problem in pure Schwarzschild case, in flat case. So we can solve a problem only if we have some cosmological problem, positive or negative, different solution, but still it is necessary to have non-zero cosmological constant. Let me remind once again the formula for Schwarzschild black hole, once again, because I already mentioned the form of Hawking temperature. Here is a Schwarzschild black hole, here is a blackening function, m is mass of black hole, Hawking temperature, and this is entropy of radiation. So we see that there is a big explosion problem with complete evaporation of a Schwarzschild black hole. Let's consider the Reisner-Nordstrom black hole. For me, today, this will be the main example. I will discuss it in more detail, in many details. And as I already said, for our case you can find in the end of my transparencies. I start from Reisner-Nordstrom black hole form of metric. It is written here. The blackening function is here. Is just this product. R plus and R minus are two horizons. M mass Q is a charge, and here R plus R minus are two horizons, and the temperature is written here. It is absolutely evident from this temperature. Then if we deal with so-called extremal case, the case when mass is equal to charge, then two horizons are coincide, and the temperature is equal to 0. So for extremal case, there is no problem at all. There is no problem at all for black hole explosion. So our proposal to solve the problem is closely related with presence of this extremal solution. In some sense, I will explain you how we can use existence of extremal solution to solve a problem. So I will show you that we can be very close to extremal charge solution, but not exactly. We can deal with near extremal charge black hole, but not exactly with extremal. Okay, let me show. I'm sorry. Well, let me show in formula what we do. First of all, a very trivial remark. It is obvious that Reisner-Nordstrom solution of an Einstein equation with two parameters, which is a solution of Einstein equation, will still be a solution if the charge is taken to dependent on the mass. It's absolutely obvious. So I can take the charge in very special form. I can take square equal to m square minus some special function. If this function is equal to 0, then we get extremal case. But here we take this function positive. Positivity is not so important. This is just for convenience. But what is important is that this function should be less than mass. Then the Hawking temperature is given by this formula. And already from this formula, we can see that if we take lambda m as O small of m square, then the temperature tends to 0 as m goes to 0. And we get the complete evaporation of black hole without without temperature goes to infinity at the end of evaporation. So in some sense, we go close to extremer case and we avoid the problem. I'm sorry, I don't know why it's so. So, okay. Let me show how it's work. Here is presented the 3D picture, which show dependence of temperature on mass and charge. This defined some surface sigma. So this is explicit form. This is a surface, two-dimensional surface in MQT space. Now we can put the constraint. What does it mean? This means that on this surface we can consider different curves depending on this function. Let me take a simplest example. Let me take the power function. Where C is a some constant. I will take it at this picture equal to 1. And let me take different gamma. If I take gamma equal to 1, then my curve goes to infinity. If I take gamma equal to 2, then my curve, then m go to 0, m goes to 0 here. I follow this curve. Then the temperature goes to some finite value. Then gamma is more than 2. For example, gamma equal to 2.5, then I will go along this curve. Of course, this line is nothing but extremal case. Extremal case. So I think that everything is obvious. Let me go to the next transparencies, where I will show you the dependence of temperature and charge, also the charge along with curve, and along with particular curve. So here is already two-dimensional picture. Our m, if we take this particular case of lambda, can be should be less than 1 because we take this constant equal to 1. And the graph shows charge for magenta and temperature versus m for different gamma. The black line, this black line shows the boundary of allowed region of M. We see that for all gamma, there is a restriction of M, and T goes to 0 as M goes to 0 for gamma more than 2. And I already mentioned this property on the previous transparencies, and goes to a constant for gamma 2 and go to infinity when gamma is less than 2. Yes, and we see that the temperature here is look like some deformed bear, some bear cutting and with on this side. Okay. We also can consider we can calculate entropy. Entropy of radiation is presented by this dark cyan line. So for gamma equal to this curve. For gamma more than 2, this curve, and less, this is not what we want to have. Also, for completeness, I presented here the dependence of free energy and black hole entropy on mass parameter. Okay, we can consider more interesting case and really look as a bell, not even the bell, but as a semicircle. We can consider from the beginning, we can assume that the temperature depends on m, like it is written here. C is some constant, we will take it equal to 1 in the moment, and some parameter m0. In this case, from this formula, I can recover the function lambda, which specified me deformation, deviation from extremality. It is given by this formula. This is nothing. This is very simple formula, but it is obvious that it's we get a real solution only if there is some constraint. I'm sorry, I cannot mark the line, only if there is this constraint. And also, if we want that temperature is positive, we also some more constraint, and m0, m0 should be less, less than some special number just because c equal 1. We can draw the picture, we can draw the graphs for dependence of this lambda, which describe a deviation from extremality as a function of lambda on these two branches, lambda plus and lambda minus. And we see that dashed red line corresponds to extremal case, and because lambda plus is more than m, then this is non-physical branch, and the blue corresponds the physical case. Then m0 is less than 0.35, like it's here, for example, 0.3, then the form of lambda looks like this. Then m0 equal to critical, then this line, instead of to be goes like this, just has a maximum here, touch this critical line, and goes back here. If m0 is more than this number, then we get our solution goes here. Then it's become complex and becomes real just for large m. So this is also not our case, not for us. Okay. Here I presented the dependence of Q square on mass. Here is absolutely evident that how to the deviation from criticality with dotted line correspond to the critical case. Q square is equal to m square, this is a parabola. Yes, and for small deviation, when m0 is 0.3, what we had with deviations look like this, but for maximum possible value of m0 is presented here. Yes. And now we can look how to find mass dependence of a temperature. It is by definition we start from this formula, and for radiation we get this formula. Dashed line corresponds to non-physical solution. What we get from this? We see that radiation entropy has a form suitable to realize the patch curve. First, when mass is bigger, possible, the biggest, is first its increase with mass decrease from some initial value. Here the value is 0, but if we use a previous case, if we use, I'm sorry, if we use this case, then it's decreased from some particular value here. Okay, but in this case, oops, it starts from 0, from this point, then increase, then decrease once again. So at mass equal to 0, in the case of full evaporation, if during evaporation we can realize the regime corresponding to our constraint, we get the page curve. So let me remind, let me say a few words about information loss problem and relation with what I said previously. The information loss problem, as it is well known, it can be formulated as follows. If a Schwarzschild black hole or another black hole is formed from pure quantum state and then evaporate completely, this means that pure state goes to mixed temperature state of radiation, and the entropy of initial pure state, which is 0, and the end of radiation, the entropy is infinity, like we has for the Schwarzschild case. So this obviously contradicts to the unitarity evolution. In our scenario, radiation entropy goes to 0, sorry, this is a mistake, goes to 0 when m goes to 0. This means that the radiation entropy follows the page curve. So we get a solution of information paradox. Okay. Now, because before I discuss only dependence on the mass, now let me discuss how it looks as it depends on time. Of course, it's in this case we have taken into account the equation for time evolution of a Reissner-Nordström black hole. The loss of massive charge during evaporation of Reissner-Nordström black hole is a subject of numerous consideration. Let me mention the first paper by Gibbons and also some other people. In this case, people use the system of 2 equations. The first equation describes the evolution of mass, and the second equation describes evolution of charge. There is almost consensus about the first equation. The first equation usually looks like this, but there are many, it is very well known form I just mentioned. This is a cross-section, sigma, and this term corresponds to electromagnetic potential. And the main discussion is about loss of a charge. But now we do not have this problem because in our case, we are in very special framework. I said that my charge totally depends on mass. So I assume that at any time of evolution, the charge is a function of mass. So, and very special function, which is written here. So I can calculate this derivative using the time dependence of mass and using the derivative of this function of m. It is not big deal to solve this problem with a corresponding equation of motion after substitution with term from here. For the case when lambda is taken to be a very simplest power function, and in this case we get this equation. With C depends on initial constant, and we left with the following solution. M0 is initial condition. This is very interesting result, because you know that if we deal with Schwarzschild black hole, consider time evolution of Schwarzschild black hole using this equation, we have no second term in this case, then there is some finite time, so-called lifetime of black hole, so finite time of black hole evaporation. But here, for this particular constraint, we get infinite large time of complete evaporation of the charged black hole for our constraint. Okay, let's try use this. So this is all what I want to say about radiation. But now it is also interesting to consider how the form of entanglement entropy will change if we consider the Reissner-Nordström under some special constraint. You know that was already, now it's already 3, maybe 4 years, there was a big activity about information paradox, where people proposed a different scenario, how to solve the information paradox. Let me just mention the paper by Pennington. And the main word or the main ingredient in all this activity is a notion of island. Island in Wundt, island take into account non-trivial topology, the topology related with wormholes in calculation of entropy, using, for example, an approach of path integral. In schematical way of the formula for entanglement entropy is presented here. Let me just say a few words here. This is island. I don't go to any detail to describe all this notation. And we have taken into account island, and we have to extremize this form, which can be written for any island. But let me, in more detail, present the answer for entanglement entropy of Reissner-Nordström in 4-dimensional case. This is generalization of entanglement entropy of Schwarzschild in 4-dimensional case, which was constructed by Hashimoto, Nizuka, and Matsuo in this paper. And in Reissner-Nordström, it was considered as in this 2 paper. In fact, we use a little bit modification version of the formula, but what is important, this is a Penrose diagram with in blue. This is an internal black hole. This is a horizon. Blue is a location of radiation, and with green is a location of island. So the island has specified by position of the end of island. We deal here with spherical symmetrical case. So the point, the end point A plus is specified by 2 coordinate, time, and A is a radius, and A minus is given by this formula, beta is inverse temperature. Yes, okay. And one can calculate in some approximation with entanglement entropy, and the answer is written here. The answer is written here. The entropy for ion depends on horizon, horizon plus, horizon minus. J is a Newtonian coupling constant. C is a central charge, and B is rotational at this point. So what do? We calculate.
You have just a couple of minutes plus the.
Okay, very good. I am going to the conclusion. So our problem is to do calculations with the help of this formula. And in this formula, what is important for me, it's important that, let me just mention this formula for maybe 3 minutes, 2 minutes, maybe it's too soon. Okay, I will try. This is the answer for Schwarzschild, for Schwarzschild case. And as we mentioned, found with Igor-Pavlovich, that when m goes to 0, then this term is increased. But this, when m goes to 0, this decrease because r is proportional to m. But unfortunately, this term is increased. So instead to get some function which just increase when m goes to infinity, we have something which goes to infinity when m becomes 0. And of course, we can say, oh, okay, here is a Planck scale. We have not to go behind the Planck scale. We have to stay outside of Planck scale. But for some special parameter, even behind even if we take m more than Planck scale, we get infinite. We get increasing. We say, and due to this fact, instead to get a typical page curve look like this, like triangle, like right and back here. Unfortunately, here is some explosion. This explosion is related with increasing of temperature, I would say, and the form is look like this. Also, let me skip this. Also, we have a similar situation if we deal with Reisner-Nordström black hole. This was considered in many detail in our paper with Igor Pavlovich and Timofey Rusalov. And we found that if we take some constraint here, a little bit different function lambda, it is written like is presented here, then only for gamma between 1 and 2, we can guarantee that we get the page curve. So to conclude, I would like to say that I tell you that the problem of black hole explosion and information loss of complete evaporation black hole are considered. So we consider to this problem. I have shown that the constraint permit to avoid the Reisner-Nordström black hole explosion. And in this curve, in this case, the page curve of radiation entropy is obtained. Similar results are obtained for Kerr-Newman, Schwarzschild, de Sitter, Reisner-Nordström, de Sitter black hole. And also we studied entanglement entropy with and without ion for Reisner-Nordström with constraint. And we discuss this as mass of black hole decrease. We shown that for special constraints, very special, where entanglement entropy does not explode as long as a mass of explorating black holes exceeds the Planck scale. So I finish here. Thank you very much for your attention. And I just show you that there are a few backup files where we can find the main rather analogous formula which work for KER. But KER is almost very similar formula, but for de Sitter and anti-de Sitter case, formula a little bit different, but I think also very interesting. Okay, thank you very much for your attention.
Thank you for the very nice talk. So we have time for a couple of questions. Does anyone have any question? I see one hand raised.
Yes. First of all, hello, Irina. Thank you for the talk. I'm a little bit curious about the following. If you have a rotating star, the Kerr solution, and it starts to radiate, why would it remain spherically symmetric?
No, as to entanglement entropy, I discuss only the Reisner-Nordström. So this is only for Reisner-Nordström. Yes, for KER, I don't know how to calculate. This is a very interesting problem to do calculations in similar way for the KER itself. This is very interesting. This is very interesting problem. So thank you for your question. Yes.
Okay, so when you said similar results, you didn't mean completely similar.
Yes, yeah. Well, very completely similar. It won't concern the entropy, not entanglement entropy. Yes. Okay.
Thank you.
So, because the similarity is here, it was the same. In this case, I put this point just in the end. Okay, sorry. Okay.
Okay, there is another hand. I cannot read the name. So, Sikander, please.
Yeah, thank you. Thank you for the talk. It's kind of a naive question, but what happens to the singularity in the black hole after black hole evaporates, either in the explosion scenario or in your scenario?
We have no, if we, let me discuss mainly about Reisner-Nordström. If we assume that we can work for the scale less than Planck scale, then we have no singularity, because we have this is very special cases. Yes.
I see. Thank you.
Thank you for your question.
Just to connect, so in your case, it does not completely evaporate, right? The black hole.
No, black hole is completely evaporated. Yes.
Ah, okay. Even in the okay.
It is completely evaporated.
Mm-hmm. Okay. So, any other question? Okay. So it completely evaporates. Okay, but it goes with the zero temperature at the end of evaporation, right? Because I understood. So it goes only when the mass goes to zero. It goes to the extremal case, right? If I understand correctly.
Yes,
so
it is, but in some special cases, goes not necessarily to zero, but to finite for finite temperature. For gamma equal to 2, it goes to finite temperature, but for other gamma, it goes to zero in the end of operation.
Okay, I see. Thank you. So, Philip, you still have the raised hand. Do you have another question, or is there?
Well, I just want to comment on the previous question about what happens if you evaporate completely. Well, you have to look at the interior solution and not just at the exterior Schwarzschild solution. And the mass is the integral of the energy density. And so if the mass is going to zero, then the energy density has to go to zero, and then you just be left with flat space. But I think that doesn't happen. I think the energy density goes to a delta function, and you never get, you will have the integral of the energy density still be zero, but it will be zero, it will be non-zero in a set of measure zero. So I don't think that you become flat space at the end.
You mean we have a central point? Maybe, yes, maybe.
Oh, right.
It is out of horizon, in fact, yes.
The horizon is zero.
Zero, yes.
It's zero radius, yes.
Yes.
Okay. So if there are no other questions, I think we can thank the Irina again for the nice talk.
Oh, thank you. Well, thank you for your attention, yes.
And we can move to the next speaker, which is Alessia Platania. Alessia, are you here?
I have stopped. I'll stop.
Yes. Alessia is.
Yes.
She's okay. She's with you. Okay, ciao Alessia. So next speaker, Alessia Platania, she's going to talk about shifting quantum black holes through the principle least action. Sorry. And do you want me to give you a reminder when you have 5 minutes left plus question, or?
Yes, give me a reminder 5 minutes before.
Okay. Okay, so you can start whenever you want.
Thanks, Francesco, for the introduction. And let me start by thanking the organizers, so Luca, Ravan, and Alex, for organizing this nice conference that put together people working on different topics, different but interrelated topics: quantum gravity, cosmology, and black holes. In my talk, I want to tell you about some recent results that they have developed recently in collaboration with Benjamin Knorr, who is also here in person in the conference. As you can understand from the title, it is about selecting proposals, alternatives to classical black holes, enforcing the principle of least action in quantum gravity. Quantum gravity, of course, is a big word that also includes and stands for several different approaches. And this comes from the fact that standard methods of standard quantization methods in quantum field theory, when applied to general relativity, they do not work straight away. And this led to a proliferation of approaches to quantum gravity. So essentially, plain GR plus QFT, perturbative QFT, does not work straightforwardly. And several approaches were developed, moving in different direction in an imaginary space of all possible direction in introducing new physics, new principles, non-perturbativity, symmetries. And of course, this does not, this picture that I'm showing is not supposed to be precise in any sense, just give you an idea of some of the approaches that have been advanced. But a key common idea of approaches is that if we want to solve the quantum theory, we need to resum quantum gravitational fluctuations. And in all of these approaches, there are certain goals, or at the moment they are wishes, because it's the context of quantum gravities are difficult to achieve. And these include mathematical consistency. So we want normalizability, unitarity, perhaps causality, Swampland criteria, and so on. We want in general to be compatible with what we see at large scales, on large scales. We want to be compatible with observations. And if we want to be even more ambitious than that, we would like also to make predictions at some point. So set up reliable computations that would allow us to explore, to predict what would be quantum, the early evolution of the universe, how quantum gravity affects the early universe cosmology. What are quantum black holes? And by quantum black holes, I don't mean necessarily black holes, but any quantum replacement of classical black holes, but of scattering amplitudes, gravitational waves, and so on. And my talk focuses on quantum black holes. So the first question that one should answer is how do we compute quantum black holes? How do we derive alternatives to classical black holes in a given approach to quantum gravity? And to compute these quantum solutions, one prior step would be to sum over all quantum gravitational fluctuations. And there are in principle alternative ways to approach the problem, but one could, for instance, very conveniently encode all quantum fluctuations in an effective action. And what I'm showing here is one specific case, so where the effective action, that is a seemingly classical action, which however encodes all quantum effects. And in this specific case that I'm showing, this comes from a functional integral over all possible metric configurations. But of course, I mean, this the specific details depend on the approach. One could have different degrees of freedom. One could have different symmetries. One could have additional dualities. At least for approaches that connect easily with quantum field theory, as this that I'm listing. In the case of steady state theories, with the theories at least that have the discrete spectrum, this might be less straightforward, but the same concepts are applicable. And I would say, I'm not an expert, but I would say this is the case for loop quantum gravity, where one can set up something similar using not canonical quantization, but spin forms. And now this approach, so regardless of how one computes this effective action, this is convenient, because once one has the effective action, then the fully quantum solutions in cosmological or black hole physics, they are just the solutions to these quantum field equations. Now, obviously, it is extremely challenging to derive the effective action, derive its coefficients, even if in certain approaches one would know how to parameterize it based on symmetry considerations and consideration based on the field content of the theory. But I mean, at the moment, the state of the art is that there are, or in most approaches, there aren't reliable approximation to the effective action. And this would be like the theory approach to finding alternative or quantum solutions to the full theory. On the other hand, in the context of phenomenology, so based on model buildings, either in quantum gravity inspired models or simply purely phenomenological approaches, some solutions, alternatives to classical black holes, have been proposed. So for instance, regular black holes, wormholes, compact objects of various types, so gravastars, boson stars, and fats balls, and so on. But now, if quantum gravity is to be the key for to achieve the singularity resolution. It is one, probably the existence of singularity was one of the reasons why one would attempt to find complete theory of quantum gravity. Then it is expected that regular black holes compact objects should arise as solutions to these fully quantum field equations. So they should arise from a principle of least action in quantum gravity. So nice. Once we are able to compute this, one could just solve this equation and derive the solutions, the corresponding solution. But one can also reverse the logic and say, given a modified solution, so something like the Schwarzschild, where the coefficients of the Schwarzschild metric plus for subleading corrections, can I come up with an effective action whose field equation give exactly this solution? And this led us to the idea of selecting proposed alternatives to classical black holes by enforcing the principle of least action in quantum gravity. And so the focus questions of this talk are the following, at least the motivations, the motivating questions. So whether one can, whether proposed alternatives to classical black holes can arise from a principle of least action in quantum gravity, and more practically, given a proposed metric, what is the corresponding effective action that can generate this solution? But now, so these questions are difficult to solve, to answer in general, because calculations are pretty involved. But some constraints, and actually I will show you that these are already strong constraints, could be extracted using just analyzing the asymptotic of the system. And I can show you two examples. Of one is a regular black hole, and one is the Simpson-Visser spacetime that can act as a regular black hole or wormhole depending on the value of this parameter. So the full these are just the lapse function or metric coefficients, so in the radial and temporal components that have this shape. But asymptotically, one can parameterize them as Schwarzschild in both cases, plus subleading corrections of the type 1/R2 something. And then you could say, okay, but this seems to be focusing on the asymptotic regime might not be enough to say something. But yeah, I mean, there are pros and cons in doing this. And the cons is obviously that one cannot really answer this question, in the sense that I cannot say, okay, I give you this solution, what is the full quantum effective action that reproduces to this solution for all covering the entire space-time. But there are a number of pros. So the results that one obtains in this case can be applied to a number of proposed solutions, alternatives to classical black holes. And also limiting to the asymptotic, one can safely say that one can use the QFT language, so in terms of an action and an effective metric. So it should, even for discrete approaches, one should, in principle, recover a QFT description at large scales. So this is the idea. Let's try to understand how to implement it in practice. And to implement it in practice as a first computation, we limited ourselves to this type of metric. So something that is static, spherically symmetric, and asymptotically flat in particular. but limiting ourselves to lapse function that can be different, metric coefficient that can be different, but admit this type of asymptotic expansion. So with the Schwarzschild term plus subleading corrections, and these coefficients CT and CR and the exponents NT and NR are different in general. And the idea is to understand whether this type of corrections can be generated by an effective action that I'm parameterizing in this form. So as Einstein-Hilbert plus higher derivatives, where there can be also form factors. So this is just the D'Alembertian, this delta is the box operator, plus higher orders. And in particular, we know that this part, the Schwarzschild part, can be reproduced by the Einstein-Hilbert part of the action. And the question is whether one can, for a given exponent, for a given coefficient in both metric coefficients, one can find certain coefficients, so certain terms in the effective action that would allow to have a field equations whose solutions are exactly a metric of this form with these scalings. So one important thing to notice is that when applying the principle of least action, so deriving the field equations, the variation acts linearly. So this means that I can consider the contribution from the various operators individually and then comparing them. And so, for instance, this would be the GR contribution. This is the R square contribution. So all of this part and so on. And if then one replaces the metric with these coefficients here in the field equations, the condition to have this as a solution is that all of these terms cancel out exactly. And I will put this equation here for your convenience. And one more thing. So we did the analysis for general values of the exponents. So NT and NR different from each other. But for presentational purposes, I will just set the two equal. One essentially obtains the same result, so it's just nicer to not to complicate too much equations in the slides. So, given this metric, how do we find corrections that cancel exactly the GR terms? Let's start with the case of a local action. This is just an ansatz. So I set the form factors to 1 or to a constant, and then I essentially compute the field equations and replace the metric with these scalings and see what happens. So from the GR term, so the first term, one would have a scaling of this form. So R to -2 minus n. And if these coefficients are constant, the form factors are constant, so one has essentially stellar gravity, then the corresponding contribution to the field equations would be R2 minus n minus 4. And if you compare these two, you can easily see that there is no way that these two terms can cancel each other. So in other words, one cannot obtain this type of solution from just GR plus stellar terms and all the rest to 0 if these are all local. Then one can also add the R cube contributions, and this would lead independent of the scaling of these two powers, would get a contribution of this form, so R minus 8. And if you compare this with this, you see that there is a way to cancel these two, and this is the case where n is 6. Because in this case, you have the same scaling, and you can just compare the two coefficients and get constraints essentially on the constants in front of your operators. But this only works with n equal to 6. So if you have a very specific scaling of these metric coefficients at large distances. And even in this case, this is just one condition, but in practice, one would also need with higher order contribution to cancel the stellar terms, or just to set the corresponding couplings to 0 to make this the full condition work. And also this condition should work on all the subleading levels. So in the case of local terms only, there is in a sense a fine-tuning of the operator. So you get strong conditions both on the exponents and on the coefficients in front of the various operators. And now I want to remind you of the examples that I have shown you at the beginning, that were the case of regular Hayward black holes and the Simpson-Bister wormholes, where the next the leading corrections to Schwarzschild goes as 1 over R24 and 1 over R23. And this means that these two spacetime, if one uses only local terms in the action, cannot come from a principle of least action. So one, of course, could say, okay, but then I can still modify this solution. So, for instance, the minimal modification to have R2 6 here would be to replace this R cube with R2 5. This is a possibility, of course, and but one needs to really modify certain some of the proposed alternatives to classical black holes. But if one wants a cancellation for generic n, and in particular, so if one really wants Hayward black hole or Bardeen black holes to come from a principle of least action with this type of scaling, then local terms only cannot do the job, and maybe one can then go for non-local form factors. But what type of non-localities do we need in order to generate these solutions? The type of non-locality that one needs is actually something of this type at quadratic order, so with 1 over box operators, or even stronger non-localities, so the type of 1 over box to n with n positive at higher orders. Because this type of corrections are those that precisely reproduce this GR scaling, R2 minus 2 minus n, and one can understand also this on dimensional grounds. And so with this type of non-localities, you can cancel the GR term for generic values of n. So even the Hayward solution and the Bardeen solutions and the Simpson-Bister spacetime could come from an effective action of this type. There would be solution. But the price that one pays for this is to introduce strong infrared non-localities. And in particular, for this specific case, it turns out that when one compares these coefficients, so essentially one sets the condition that this plus this plus this is equal to 0 to have this as a solution, one gets some very specific coefficients, alpha and beta, that satisfy this expression. And then if one computes the 2-point function from this action, one obtains a vanishing 2-point function, so a diverging graviton propagator. That is not nice. One would not have gravitational waves, essentially. Alternatively, one can just go, avoid this by introducing this type of non-localities, but stronger at higher order in the derivative expansion. But this cures one problem, that is this, the vanishing 2-point function. but really has to introduce strong infrared non-localities that most probably are already at odds with observations. So aside from specific values of n, most of the proposed alternatives to classical schwarzschild black holes, under our assumption of spherical symmetry, asymptotic flatness, and so on, essentially require large distance non-localities, and this includes Hayward and Bardeen black holes, for instance. And an exception is the Dimnikova black hole, or anything having metric coefficients involving the transcendental function, because these typically do not admit an asymptotic expansion, so our arguments simply do not apply. And now I can go to my summary and conclusions. So what one would like in the, so typically the transition from GR to a full theory of quantum gravity and matter, it is expected that the classical black holes, which are singular, are replaced by regular objects that can be regular black holes, they can be wormholes, compact objects, and so on. And the idea of our work was to select these proposed alternatives, this type of proposed alternative classical black holes, by enforcing that this comes from a principle of least action in quantum gravity. And we did so by focusing on a large distance regime, where well, calculations are still involved, but doable with respect of the full case. And one gets some conditions that are already pretty strong. Of course, if one could be able to have the full answer to this, to the question of having of constraining of reconstructing the effective action from a certain solution, one would have even stronger additional constraints. But on the other hand, this analysis is convenient because, I mean, there are some advantages because it is expected that at large distances, one independent of the specific theory of quantum gravity would recover standard concept in quantum field theory. So one could really safely use the concept of effective action and effective geometry, even for discrete theories of quantum gravity. And we studied the case, we made certain assumptions to start. And these are like asymptotically flat spacetimes, static, spherical symmetry, and we focused on metrics whose coefficient admit an asymptotic expansion. And we found that if one uses only local terms, then there is a sort of fine-tuning. So not all type of asymptotic scaling would work. Not all of them could come from a principle of least action in quantum gravity. And if one really wants certain black hole solutions or compact objects to arise from a principle of least action, one needs to introduce non-local terms. But the type of non-local terms that one needs to introduce are those of 1 over box 2n form. So strong infrared non-localities that would lead to large distance modifications of GR. And essentially, if our analysis would extend also to the case of the rotating case, also with a cosmological constant, this would already allow to rule out some of the proposed alternatives to classical black holes, simply based on asymptotic considerations. So it's not obvious that asymptotically one would have something that is consistent. It's not really necessary to go inside a black hole or close to the regions where quantum gravity effects would be important to get strong constraints. And with this, I thank you for your attention, and I'm looking forward to your questions and comments.
Thank you, Alessia, for the very nice talk. I see there is already Philip who wants to ask a question. Please go ahead.
Well, first of all, Alessia, thank you for your presentation. I found it very interesting, but I have a question which I hope you'll not think I'm trying to be too critical. First of all, let me ask you, the solutions that you gave at the beginning, the one by Hayward and the one by Simpson and Visser, where did they get them from? Yes, where did they come from?
They are just phenomenological models. So, for instance, the Hayward solution, as well as the Bardeen solution, they are probably the simplest solution that can, by which you can achieve a singularity resolution. And by the simplest, I mean that the exponent here is the lowest, such that the curvature invariants, like the Kreshman scalar, are not singular at r equal to 0.
Oh, I see. So it's not necessarily, it's not a solution to the Einstein equations, even with R squared type terms. It's just a statement about what we think such solutions might look like.
Yes, they are just phenomenological models. They are not a solution to anything, or at least so some of these solutions, I don't remember which one, you can find them as a solution to GR plus nonlinear electrodynamics, but or some other modification involving magnetic monopoles, but you really have to do something in the matter, something weird in the matter sector to achieve them.
Okay, all right. Now, so that's why you may not make contact with their solutions at all R, but possibly at large R. So now I'm trying to understand whether what you've done has anything to do with quantum gravity at all. I mean, if you just took your action with the R squared, and the F of delta, whatever it is, as the classical action of gravity, and you did the stationarity with respect to the metric and asked for the vacuum solution, you would have got the solutions that you got. So you can get, I mean, what you've done is a completely classical calculation using a classical action. Now, the only, at least I think that's what you've done, the only place that quantum gravity could come in is if the correction terms to R in your action were themselves generated by quantum loops.
Precisely.
But you didn't demonstrate that that would be the case. You never gave us any loop calculation that would have produced any of the F of R or F of RIC deltas that you used.
Of course.
So I'm not sure that I've yet followed the logic, but maybe this is something you're working toward.
So the point is the following. So you have your classical action. Once you start introducing quantum fluctuations, so quantum gravitational fluctuation, you will have corrections. Corrections that can be parameterized by these form factors. So, for instance, in a one loop calculation, you would get here logs, right? Depending on the theory of quantum gravity you are working on, so these form factors will be different. They really depend on the specific theory of quantum gravity. So what I'm saying here is I'm not doing a first principle calculation, because I'm just reversing the logic. So I say that I'm doing a quantum gravity fluctuations, and I come up with an effective action of this form, where these are some form factors that come from having resummed quantum fluctuations along all scales. Is there any of the proposed phenomenological models of black holes or compact objects that can come potentially from an effective action of this type.
Okay, so would you define a quantum black hole as one that only comes from the corrections to R, and a classical black hole as one that comes from R itself?
Well, I've been defining the classical black holes as black holes in general relativity, and quantum black holes or quantum, I don't know if it will be a compact object or whatever, the solution to the full quantum theory. And the full quantum theory that is here parameterized by the effective action. So in say in a theory that is just in a metric approach to quantum gravity, where you have diffeomorphism invariance, so the effective action would be the result of a functional integral. And then the quantum solutions are just the solutions to the fully dressed field equations.
Okay.
I don't know if the answer to your question.
Yes. It's just that the problem is that whenever people do quantum gravity, they always said h bar equals 1. And so when you wrote your expansion, you didn't show it was an expansion in powers of h bar. So there could have been classical terms all along, or they could have been generated by quantum fluctuations. But if the quantum fluctuations, then they're going to depend on Planck's constant.
In general, I mean, if you resum loops or do a full non-perturbative calculation, h bar will be, I mean, hidden in these terms. So there will be both classical terms and higher, I mean, terms that are purely come from integrating out quantum fluctuations. And what I'm saying is this is something that could come from quantum gravity. So there will be higher derivative corrections that also encodes the physical running, essentially, the momentum dependence of the couplings.
Okay.
And the point is trying to understand if some proposed alternatives to classical black holes can in principle come from an action principle. Because if they can't at all, then probably they can't come from quantum gravity.
Okay.
Not a full, of course, answer, but.
Okay. So Luca tells me that there is a question from an on-site participant, and then we go to Sravan after that.
There is a question.
Yeah.
Yes, Shapiro. Yeah, I not question. I have to make some observations. So as you said, these form factors, they depend on the model for quantum gravity which you work with. Okay. So if you work with Einstein gravity, this form factor both completely depends on the choice of the gauge fixing and parameterization of quantum method. In particular, you can choose gauge fixing or parameterization in quantum metric such that both form factor simply vanish. It's not difficult. It's known from 78. Okay, then if you work with force derivative gravity, classical force derivative gravity, then there will be invariant form factor between square of the Weyl tensor and Weyl tensor form factor will not depend on the gauge fixing or parameterization, but in this case, you probably cannot write this way. You have to write R plus square of the Weyl tensor classical plus square of the R square classical, and then you have your form factor, and once again, second form factor FR without indexes will depend on the gauge fixing and parameterization. Okay, if you want choose your gravity theory, quantum gravity theory, such that this form factor do not depend on the gauge fixing parameterization, then your classical action must have at least 6 derivatives. If your classical action has 6 derivatives, then you are fine. But then all this makes no much sense because you have classical terms which dominate strongly in the ultraviolet, as you say that you want ultraviolet, okay, if you want ultraviolet, then they will dominate about these form factors horribly. Now, if you want to go to the infrared, once again, it's difficult, okay? Then to understand. And finally, I don't know the theory which gives you 1/box. Well, as you said, logarithm is typical for the massless theories like photon or graviton. You can use what we did in the last papers with Tiberio and Breno, Gicini, Tiberio, Neto. You can use Wilkowski-Dewitt approach, for example. Then you have both form factors invariant. They don't depend on anything. Okay, the formulas are known. You can take, for example, from paper of Barvinsky-Wilkowski in '85, and we recalculated recently and so on and so forth. Okay, but then you have to like this, and you have logarithmic form factors. If you want to take contributions from matter fields, from quantum matter fields, which is also very interesting, then we calculated 2003 with Eduard Gorberg from Kiev, and then the formulas are known, but it's not logarithmic. They become logarithmic in the ultraviolet, and they decouple, disappear in the infrared. Okay. So this is the state of art for one loop calculations. If you want to go beyond one loop, then it's more complicated.
But that was really a lot of comments on which I could comment on. So first of all, in a non-perturbative setup, you would expect the Bayer action to also contain infinitely many terms, not only like GR terms or R squared terms. There will be many, even more.
Non-perturbative, you mean functionalization group?
Not necessarily. I mean, also if you set up like a lattice computation that is non-perturbative, right? I mean, you are evaluating the full path integral theoretically. I mean, I'm not saying that it is doable, but
you want to say that in lattice formulation you can calculate form factors, really?
You can't, you can't like analytically, but you can compare FRG calculations, for instance, with their profile functions and extract the corresponding form factor that Benjamin did a couple of years ago.
Okay.
And I'm aware, of course, that if you do calculation at one loop, you get logarithms. I agree. But what we wanted to do here was not to say how the form factors should look like according to quantum gravity. We only wanted to say, like, let's start from phenomenological models that have been proposed. Like, what would be the corresponding form factors? And then one gets something like 1/box. And it is not obvious at all that that kind of thing would come from any theory of quantum gravity. The only statement is if you say that Hayward black holes are your final solutions because, I mean, there is any experimental evidence for that, then you would need that type of operators in your action in order to generate them from a principle of least action. But of course, it is possible that Hayward is not the replacement to classical black holes. It is something else, and then you would have different form factors, and in particular, the form factors that come from a fundamental theory of quantum gravity.
There is also another question from the audience. Please, I don't know if it's okay.
Yeah. I mean, Zdravin is one organizer, so we can keep him last.
Okay, so I have a question, and thanks for your nice talk. Let me first make an observation and then actually a question for you. So the observation is that you see when you have this non-local action of terms quadratic grid in Ricci, it's just kind of, I mean, a Ricci scalar or Ricci tensor, it's just kind of natural to expect that it would be very difficult to get different solutions than a Ricci flat solutions. And what you have in your functions, they, I mean, without the C and C coefficients, this were of course Ricci flat metric. I mean, it was the Schwarzschild one, and I mean, this is obvious fine, but you can read it also in our paper that yes, if you start with the expansion which is quadratic in Ricci scalar or quadratic in a Ricci tensor, of course, all the things which are Ricci flat, they are in vacuum natural solutions. So that's why kind of explains why you may maybe originally you have thought that there will be some hope, but at the end you find that at least for local terms you are not able to find any any action that produces this term. So this is an observation. And then probably you have had a discussion yesterday when some people were criticizing the action of this type. So okay, I don't want to repeat the criticism, but let me ask what is your opinion and how you would defend yourself for the same objections that were put to the Javier's talk last time.
So first a comment on the first part. So I'm not sure that in the full theory you would have a Ricci flat solution, because we know, so we thought about that, and but in even a simple like loop calculation, you would easily see that a bunch of higher derivatives terms are generated, in particular the Gorov-Sognotti terms, and this would make it impossible to have a
they will be in this master term, because you can write them as actually without taking all the traces as by Q. So that's important, exactly, because they are not quadratic in Ricci tensor.
Yes, and regarding the other part, so essentially unitarity. So the point is that one should not truncate. Ideally, of course, you do so to make calculations doable. But even if you need to truncate and you generate ghosts that perhaps are not there in the full theory. So there is a paper that I put out a couple of years ago now with Christoph Wetterich. And there we show that this type of ghosts that are fictitious, that are not in the full theory, they will automatically decouple from the theory, because their residue gets smaller and smaller. The residue of the propagator computed at the corresponding pole gets smaller and smaller as you include more and more terms in your action, and so they automatically decouple, and at some point, if you introduce a sufficiently large number of terms in your action, they are essentially harmless. So they just decouple from the theory automatically.
Yeah, so it's nice to answer, right? It could be also added to yesterday's discussion.
Yes.
Yeah. Okay, thank you.
Yes, could I just add a very quick comment on yesterday's discussion? One of the questions that you could ask of the classical theory with these extended black hole solutions is you take a scalar field propagating in this background and you ask, does the propagator take support outside the light cone? Because that would be evidence of an instability without getting into the issue of quantization. I mean, I think that's a very clear cut, because that would basically say you've got a tachyon.
Well, whether there is actually a ghost or a tachyon or any other additional degrees of freedom also depends on the specific shape of these functions.
Yes. So the question is, are there choices of F for which the propagator does not take support outside the light cone, and are there choices of F for which it does? That was all I was asking.
2-3 examples that I know. There are many examples in the literature. So in local gravity or slash infrared of string theory, they have these exponential form factors. In a previous paper from a couple of years ago by Frank Zaoressig, Benjamin Knorr, and Chris Ripken. So they have also put forth a specific form factor involving hyperbolic and hyperbolic tangent, if I remember correctly, which is compatible both with unitarity bounds and with scaling variance in the UV, so renormalizability a la Wilson. I mean, there are a couple of examples where you can achieve all of these.
Okay, very good.
Okay, we can continue the discussion during the discussion session. So we will we start the discussion session with the Sravan question. And thank you again, Alessia, for the talk. Okay, so let's move to the next speaker, Gonzalo Olmo. Are you here?
Yes, I'm here.
Yes. Okay, can you try to share the screen?
Yes. This one. Okay, it's almost there. Okay, can you see the full screen now?
I can. It's still not full screen, but
it shouldn't take long. I just did it. Is it working or not?
No, it's not full screen.
Okay, so just give me a second. And now?
No. I mean, it's
Well,
okay, but if we can have full screen, it would be better.
Anyway, so but it is big enough because
yeah, I think it's big enough. I'm not sure that maybe it's cutting some small part of the slide in the bottom. I'm not sure. Can you change slide just to check? No, okay. You can see. We can see all the slide. I think it's fine. Yeah.
Okay, so let me see. Well,
yeah, it's okay.
Maybe if you can zoom out a bit, maybe it's better.
Zoom out. Ah, okay.
Zoom out.
No, it's always the same because I'm changing the zoom. No, I see that it's always the same in your screen is somehow.
Yeah,
maybe yeah. So let me just reduce it a bit.
Okay, good. That's good.
Okay, is that okay? Okay.
Okay. So do you want a reminder 5 minutes before the end of the talk, or?
Yes, probably because sometimes I speak, I speak too much.
Okay, I'll give you a reminder. Okay, so let's go now. The next talk, as I said, by Gonzalo Olmo. He will talk about metric affine Chern-Simons modified gravity. So yeah, feel free to start as soon as you're ready.
So thank you, Francesco, for the introduction and for taking care of the session and the organizers for the invitation. So today I want to present a work I've done in collaboration with Simon Boudet in Trento and Flavio Bacino in Valencia and Paulo Porfirio in João Pessoa in Brazil. So it's about Chern-Simons modified gravity, but in a metric affine formulation. Okay, I will try to justify the title first of all to motivate everything. So first thing is that I'm going to focus on aspects related to quantum or to compact objects in this talk. So mainly because nowadays we have access to data about the propagation of electromagnetic waves, electromagnetic radiation in the neighborhood of compact objects, thanks to the very large baseline interferometry of the Event Horizon Telescope. We also have gravitational waves coming from compact objects, thanks to the LIGO and Virgo observatories. And despite this new data that we have for the first time in history, which is very good, we still don't have a clear understanding of the nature of the compact objects that generate these phenomena. Of course, we have favorite candidates. Black holes are always there, but who knows? There are billions of galaxies, and if we have to check that every galaxy at the center has a black hole, we have to look at all of them. So the fact that we observe something that is compatible with a black hole doesn't rule out other possibilities. So, and nowadays in the literature, we are all very creative, and there are many alternatives to black holes, such as wormholes, we have stars, and other objects. So if we eventually end up ruling out, imagine, black holes, then our understanding of quantum gravity would be completely would need an important modification. Okay, so it is fundamental to continue exploring, to analyze data, and really to confirm our basic assumptions about nature and compact objects. So, and in this sense, I'm now trying to learn a bit more about the observational characterization of compact objects, and this is why I'm presenting this work. So first thing is to explain why I'm considering Chern-Simons theory. Well, always considering modified theories of gravity is interesting because it provides new perspectives on well-known problems. And in the case of Chern-Simons modified gravity, we have the special ingredient of this theory is that it allows to implement parity violations in gravitational scenarios. Okay, this is something that is interesting on its own, and this kind of model implements that effect. So where does this Chern-Simons theory comes from? Well, Chern-Simons terms are important when one deals with gauge theories and quantize these gauge theories. So Chern-Simons terms are necessary in order to give consistency, quantum consistency to the full theory, in order to get rid of anomalies or cure or interpret correctly these anomalies. And when one considers gravitation as a gauge theory, so this kind of Chern-Simons gravitational terms arise. Okay, more reasons arise because also radiative corrections with quantum effects, with gravitational effects, also induced Chern-Simons terms. In the low energy limits of string theories, it is possible to show that Chern-Simons terms arise. Also, when one considers, for instance, loop quantum gravity and analyzes the coupling of fermions, then you need, for the consistency of the implementation, if you want to recover the Einstein-Cartan theory in the classical limit, it is necessary to introduce a Nye-Yang correction. And if, in addition, you make dynamical this the barbarionicity parameter, then it is necessary to introduce a new Chern-Simons term. So every time you play with gravity and quantum theory, in the end, for some reason or another, you end up needing Chern-Simons terms. And also, if you play with Lovelock theories, which are second-order theories, the most general second-order theories in different dimensions, if you relax the condition on the torsion and you allow the theory to have torsion, because the usual Lovelock theory assumes a pure metric background, if you allow for torsion, then you see that besides the usual curvature corrections, curvature terms for the Lovelock theories, new terms like Nye-Yang terms and Chern-Simons terms, they all are permitted according to the basic assumptions for Lovelock theories, the second-order equations and all that. So these terms seem to be everywhere from different perspectives. Okay. So, and why do we need to modify Chern-Simons? This is better explained with an example. If you consider in 4 dimensions a Chern-Simons term, gravitational term, you have something like this. This is the Pontryagin term, the quadratic Riemann contribution constructed using the antisymmetric tensor, the epsilon. So essentially you have the dual of the Riemann contracted with the Riemann. And this quantity is what we call a Chern-Simons term, and it can be written as a total derivative of a vector. And as such, if we just write the theory like this, so this is a total divergence, and it doesn't contribute to the field equations. It's like the Gauss-Bonnet term, for instance, in 4 dimensions, it doesn't contribute to the field equations. Okay, so if we want this object to participate in the 4-dimensional dynamics, we need to take one of the coupling constants, this theta here, and introduce it, promote it to a scalar field. Okay, so when this is a function, it's a scalar, no longer a constant, then integration by parts of the total derivative is no longer a total derivative. And then we have a term that contributes to the field equations. And this is how you can introduce these the effects of symmetry breaking, of parity violation in the gravitational 4-dimensional dynamics via the Chern-Simons term. You need this coupling with the scalar. And once you introduce this coupling, it is natural or reasonable or possible to admit that the scalar theta has some dynamics. So it can have a kinetic term and maybe a potential. Usually the potential is neglected and only the kinetic term is considered. So this modification of general relativity, so essentially we have general relativity with this modified Chern-Simons theory, was originally proposed by Jacques and Pai in 2003. And then there was a lot of research, and Alexander and Younes wrote a nice review in 2009. And if you want to know more about Chern-Simons theory, I recommend you these lecture notes by Sanel. So this way of promoting the Chern-Simons, the standard Chern-Simons term, to play some role in the dynamics of 4 dimensions is quite standard, because you are probably familiar, have heard about Gauss-Bonnet theories in 4 dimensions. They don't contribute to the dynamics. But if you couple the Gauss-Bonnet term to a scalar, then you have modified dynamics. This has been explored in many papers. Or even if you consider a function of the Gauss-Bonnet term, you also get new dynamics. So you can do the same with the Chern-Simons corrections or with the Nie-Yang terms. Okay, so this is quite a standard to extend the theory or modify general relativity with this style of trick. Okay, so the last part is why the metric-affine formulation. Okay, we have Chern-Simons, the modified Chern-Simons, and now an additional modification from the standard analysis, which is the metric-affine formulation. So the metric-affine formulation assumes that metric and connection are independent geometric entities, and so there is no a priori relation between the metric and the connection. So then the connection is not forced to be metric compatible. Okay, so it can have torsion and it can have non-metricity. And in this sense, there is no reason why a geometric theory of gravity should not be formulated in a metric-affine scenario, because there are no experiments that rule out this type of geometries. There are no experiments ruling out the possibility of torsion or of non-metricity. Okay, so even if general relativity, the standard formulation, is compatible with observations, who knows if the geometric gravitational framework should be enlarged for some reasons. Okay, so in this sense, we need reasons. Okay, and one of the reasons to enlarge the geometric scenario to the connection, to an independent connection, is from the fact that the coupling between matter and geometry is with fermions. I mean, matter is represented by fermions, the quarks and the leptons and quarks, is via torsion. So if we want to build a complete theory or a more general theory of gravity, so we need to explore all the possible couplings between matter and geometry. So we need to give some freedom, or more freedom than general relativity, to these couplings between fermions and torsion. So a natural scenario could be an Einstein-Cartan framework, but the metric-affine is even larger. So it's natural to consider that case also. Also, if at very high energies you assume that physics should be scale invariant or conformally invariant, then this could require the introduction of non-metricity. So essentially, the Weil theory was based on a special kind of non-metricity. So a more general theory could also include this aspect of metric-affine geometries that is not contained in Einstein-Cartan spaces. So that is another reason why these metric-affine scenarios are reasonable. And as I mentioned before, many different approaches to quantum gravity suggest that Nie-Yang or Chern-Simons terms should be included in the effective actions. And when one formulates Gauss-Bonnet theories in Einstein-Cartan spaces, naturally it finds that those terms, the Chern-Simons terms and Nie-Yang terms, arise naturally in log-log theories. So maybe quantum gravity or quantum approaches to gravity are telling us that those geometric elements are necessary from the beginning. So maybe we should start from the very beginning with metric-affine geometries and then consider quantization. Okay, not to quantize and then see that we were missing some terms. Okay, and also there is another reason, more practical, more phenomenological, and it's the fact that metric-affine geometries do exist in nature, even if they are effective descriptions of condensed matter systems, but crystals systems with a microstructure like crystals, which contain defects, they all, in the continuum limit, the propagation of waves in those media require the use of metric affine geometries. So because torsion is the continuum description of these locations, and non-metricity represents point-like defects. So this is well known in condensed matter and is essential in metallurgy. So if you want to build suspension wires for noise reduction systems in gravitational wave detectors, for instance, you need to know very well how your wires are constructed and the elasticity and plasticity properties. So, and you need to use the properties of metric affine geometries to see how waves and perturbations propagate in this media. So I think that metric affine geometries are well justified, and we are all going to put everything together with this Chern-Simons modified theory, essentially to see what happens, okay, to see what new effects we can observe in black hole scenarios. And before going into the details, it is important to note that once we consider that metric and connection are independent entities, so it's natural to ask about symmetries. So are there transformations that affect only the connection, not the metric, and that may play a relevant role in these gravitational scenarios, in these field theory scenarios? And the answer is yes. In particular, we need to pay attention to projective invariance. This is a transformation of the connection that is well known from the early years of the 20th century, when non-Riemannian geometries were first studied. And essentially, this symmetry is an invariance that arises when one studies geodesics, how a given manifold is covered by geodesics. So reparametrization invariance is related to this kind of transformation of the connection, okay? So any two connections related by this transformation generate the same set of paths, the same set of geodesics, okay, up to reparametrizations. So these kind of transformations do not live invariant the Riemann tensor, okay? They have this transformation law, this one form generates a kind of field strength, antisymmetric field strength, and the Ricci tensor of this object built by contracting the rho sigma indices is also not invariant. But if we consider the contraction of the Ricci with the metric, like in general relativity, we see that the resulting Ricci scalar is invariant under projective transformation. So this is a symmetry of the Einstein-Palatini version of general relativity. Okay, so this is a new symmetry. As a symmetry, it involves, it allows to simplify the equations. In particular, it shows that the Einstein-Palatini theory does not provide enough equations to solve 4 degrees of freedom of the connection. And this allows to simplify the connection and essentially simplifies everything. So, but when one goes beyond general relativity and considers other theories of gravity in the metric affine formulation, projective invariance is not only useful to reduce the number of degrees of freedom and simplify the solution of the equations. It is also very important to avoid ghosts, okay? Because metric affine theories typically have second-order equations, but that is not enough to avoid ghost-like instabilities, okay? But it has been observed that at least in some families, large families of theories, if you impose projective invariance, then ghosts are avoided, okay? Which is something that must be investigated further to see how far this result goes. Okay, so projective invariance is very important. So when we consider the modified version of Chern-Simons gravity, which is this one, this is the traditional form in the metric formulation of modified Chern-Simons gravity, we see immediately that in the metric affine case, this quantity is not projective, it's not invariant under projective transformation. So we need to improve the theory, okay? if we want to impose that symmetry. So there are different ways to do it, but and we have chosen this one. So essentially, we keep this part, which is this side here, and then we add this calligraphic R quadratic term. This calligraphic R is simply the contraction of the two first indices of the Riemann. Okay, it's not the Ricci. The Ricci is the first and the third, or the first and the fourth. This is the first and the second. Okay, so this calligraphic R is called the homothetic Ricci curvature. Essentially, this is an antisymmetric object, and it's necessary to compensate for the anomalous transformation of the Riemann and the projective transformation. So these two guys implement the symmetry. Okay, and in addition, this particular contribution with the 1/4 here can also be written as a total derivative. Okay, so the whole action admits this. If theta were constant, then the whole action would be this contribution would be topologically invariant. So a total derivative that would not contribute to the field equations. Okay, very good. So this theory and the manipulations to lead to this invariant theory appear in this paper. So you can look at it for more details. And now what we have to do, since we have the theory and we have the action, we just need to look at the equations and consider applications. Okay. So before entering into details, so just note that the Ricci scalar is the standard part of general relativity. So this R is the contraction of the metric, the inverse metric with the Ricci. And then we have the Chern-Simons terms, but note that the epsilon, the antisymmetric tensor has 1/√(-g). So that cancels with the √(-g) of the volume element. So everything on related to the Chern-Simons contribution does not depend on the metric. So there is no metric dependence in that part, only connection dependence in there. So this term, the theta dependent terms, will appear in the connection equation, not in the metric equation. The theta may appear through the kinetic term of the scalar field, okay, not through the Chern-Simons contribution, okay. And so later we will see the equations in detail. But now, just since we are the newest element in this theory is the right-hand side of the equation. So the left-hand side for the connection equation is the same as in general relativity, and the right-hand side in GR is 0, because that happens when this theta is constant. Okay, when that guy is constant, the Chern-Simons contributions are topological, so they do not appear in the field equations. But when this is a non-constant quantity, the right-hand side is modified. Okay, so this complicates the solution. So we don't know how to solve this equation in general, or it was not known. In general relativity, we do know how to solve it. In particular, the projective invariance allows to simplify or trivialize the torsional part, so that we end up with the usual metric compatibility condition. And but now things are different. So if you pay attention to the left-hand side, we have the covariant derivatives will introduce a linear connection, terms with the connection, you know, the gamma G. Torsion is also constructed with the connection, it's linear in the connection, it's the antisymmetric part. But the right-hand side has the Riemann tensor, so it has quadratic terms in the connection and a partial derivative of the connection. So we don't have second-order equation or second derivatives of the connection here in this equation. So do not expect to find dynamical elements in the connection. Okay. What we do have is a constraint equation, more complicated than in GR. In general relativity, as I said, only the connection appears with the metric and derivatives of the metric, so that we can solve everything in terms of the Levi-Civita solution connection. But now the equation is more difficult, so there will be some algebraic relation between the connection, the first derivative, and these other elements. So in general, this is going to be a more difficult problem. So we do have methods to solve for the connection in some theories, like f of r theories, theories that depend on the Ricci tensor in general, not just the Ricci scalar. But when the Riemann appears in the Lagrangian, there are no generic algorithms to solve for the connection. Okay, so we need to use our imagination, as I say here. So in general, it's a difficult problem. And well, you can try to decompose the connection in terms of the Levi-Civita part plus other things related to torsion and non-metricity. This is torsion, as I said, antisymmetric part. Non-metricity is defined like this, in this way. Then you can decompose torsion and non-metricity in its irreducible parts, and then put all that in the equations and play with them and spend some time. Use the projective transformation properties to impose some useful gates, such that the torsion, for instance, this vector associated to torsion is 0. You can do all those things, okay, and manipulate things and blah, blah, blah. And what we did is summarized in this picture, okay? So this is a roadmap to solving the connection equations. So the previous 3 slides represent this part of the map, okay? Everything is under control. We have the irreducible representations. We have the nice vectors, the tensorial parts of the connection, which are traceless. We do not have axial component. Everything is very nice. And you can do that. You can introduce all that. You get useful simplified equations because we are separating different elements. But in the end, things get very messy and complicated. So if you want really to progress and get a full picture of the theory, you need to sacrifice something, okay? So we adopt a perturbative approach. So more or less, you see that this animal that looked like a mammal is in fact a mammal. It has 4 legs. But you don't really know if it is a horse or a unicorn or something in between, a llama or whatever. So the point is that we have to sacrifice something. We have to proceed perturbatively and do our best to extract the physics of the problem, okay? So, and this is what we do, essentially. Just going quickly through this, all this, you know how to compute perturbations. You just consider the metric with some background, perturbations, the scalar, we assume a constant background, and then contributions, in such a way that when the scalar is constant, the solution, the background solution for the connection is just Levi-Civita of the background metric, okay? And then with that, we can proceed perturbatively, and what we get is that the vectors associated to non-metricity and even the tensorial part of non-metricity is 0 to the leading order, to the first order in the corrections, and only the torsional terms contribute, okay? In such that this axial part, if you put it to the on the left-hand side, what you get is the torsion tensor is given by this quantity. Okay, it's linear in the derivative of theta, and depends on the background, on the Riemann of the background metric. Okay, so what we do now is just compute the perturbations of the other equations, in particular the variation of the metric. Looks like general relativity, but referred to the connection, the full connection, and computing this perturbative expansion. So we have GR as the background. The first order corrections is the usual perturbative term of the Einstein tensor, plus an additional contribution that comes from the torsion, from the connection parts. Okay, so this C mu, this C tensor, is given by the torsion. And then we have the scalar field equation. Okay, as I said, the kinetic term depends on the beta parameter. But as we will see, even if beta is 0, we do have dynamics for this scalar. Okay, so with this, the whole set of perturbative equations will focus on Schwarzschild background, which is the simplest, of course. and we get something non-trivial, which is sufficiently good, okay? Because sometimes you focus on the simplest scenario and you don't get anything, but we do get something, okay? So the point is that we just need to apply the full machinery of perturbations in spherically symmetric scenarios. You are probably familiar with it. Just note that the scalar field perturbation is now going to be represented by this capital theta function. And the metric perturbations are the usual, have the usual notation. We use the Regge-Wheeler gates and have the polar and axial perturbations. And what we find is that the polar perturbations are not affected by the scalar contribution, and only the axial elements are affected by the Chern-Simons theory. Okay, so well, the axial part, the polar part is the same as in metric formulation of Chern-Simons, but the axial part is different. Okay, so we are going to focus on that. Okay, so manipulating all the equations, we end up with an equation for the perturbation of the Chern-Simons scalar, and an equation for this variable that represents the axial metric perturbation. Okay, it's, the relation with the Regge-Wheeler variables is given here. This is quite standard. This f function is just the Schwarzschild non-trivial function. Okay, and then we have several potentials here: V affecting the metric perturbation and W affecting the scalar perturbation. It is important to pay attention to omega-1 and omega-3. This T and omega-4 is something, no, not omega. Omega-1 is important because it depends on the parameter beta. Okay, so note that when beta is 0, we still have a non-zero coefficient here. So this is why we have dynamics. In the metric formulation of Chern-Simons theory, the beta equal to 0 case is pathological because it is not a dynamical equation, it's just a constraint equation. So you cannot decouple axial and polar perturbations. The equations are messy, you cannot really solve them. But in the, so you need to consider the non-zero values of beta if you want to do something reasonable. But here in the metric affine formulation, even if beta is 0, the equations are dynamical and well behaved. Even though, as we will see, the physical effects are different. When beta is 0, strictly 0, then the asymptotic form of the potentials changes, and this has an impact on the quasi-normal modes. So we are going to
Sorry, you have 5 minutes.
Thank you. So we are going to study the quasi-normal modes. Essentially, what we find is that the scalar equation is characterized by just one frequency, while the metric perturbation is described in terms of two frequencies. One that corresponds to the tensorial mode, and another that is exactly the same, the scalar mode frequency. So because the equations are coupled, if you remember. So the equation is here. So the scalar appears in the metric perturbation. So the frequency of the scalar field of the scalar mode influences the quasi-normal modes of the tensorial perturbation. So these frequencies, these numbers, coincide with the L equal to 2 modes in general relativity. And we find different behaviors when, depending on the value of beta. So when beta is large, the scalar field is essentially decoupled, and the metric perturbation has an interference between the two frequencies, then the proper tensorial one and the scalar one. When beta is smaller, then the scalar field begins to have also an interference, but the frequencies of the quasi-normal modes are the same. And when beta is really small, then frequencies begin to change, and the two are oscillating with these two frequencies. Okay. The behavior is the standard one. So you have the quasi-normal mode oscillations, and at late times you have these power law tails. Okay. We can compare our results with general relativity and with the metric formulation of Chern-Simons. So the blue dots correspond to our theory. The yellow ones are the metric version that we took the data from this paper. And the black solid and dust curves represent the results from general relativity, okay? As you can see in GR, there is no beta dependence. So this axis represents the dependence on beta from large beta to 0 here. So as you can see, the scalar and tensor frequencies separate as the value of beta becomes smaller. And in the metric case, there are no oscillation modes for beta smaller than 1/2. Okay, this is why they are not represented here. So in our case, we do have oscillations for any value of beta, even for beta 0. So from the point of view of observations, if we can measure oscillating modes, scalar mode and tensorial mode for any value of beta in the metric affine formulation, which is different from what you get in the metric formulation of the theory. And an important aspect is that when beta, in general, for finite values of beta, the power law tails coincide with general relativity, with expectations from GR and from the metric version of Chern-Simons theory. But when beta is 0, then this power law tail is different. Okay, in GR is given the power, the T mu has this analytical expression, and for beta 0 we find a correction. Okay, so this is different from the expectations from GR. So this is a clear signal that the theory is predicting something different. So it can be ruled out essentially. If we were able to measure these power law tails and the frequencies of the quasi-normal modes, then there would be a chance to rule out this theory, okay, or to confirm, but that would be too lucky. So just to conclude, we have analyzed a modified theory, which is based on geometric principles motivated by gauge symmetries and other aspects of quantum gravity. This is Chern-Simons theory formulated in the metric affine approach. We got new equations which were difficult to solve, so we decided to follow a perturbative approach, but that was good enough because we got interesting observational results that allowed to distinguish this theory from general relativity and the metric version of the theory. So even though the approach, we couldn't really finish the horse as we wanted, we got some interesting results, and this is what we have. That's it. Thank you.
Thank you for the very nice talk. We have some time for questions. So I see there are a few hands raised. So the first one, I think it was Alberto, and I cannot read the surname. Alberto Salvio, so please.
Yes. Thank you for the talk. I have a question regarding your statement. If I remember correctly, you said at some point that since the equations of motion for gamma are first order, then you would expect gamma not to be dynamical.
Yes.
Is that true?
I say yes. Yes, these are the equations for the connection. So in GR, the gamma is not dynamical, it's constrained, and it gives the Levi-Civita solution. And here we have only first derivatives of gamma in the region. So there are no second derivatives of gamma, so this is not a typical dynamical equation for the connection. Okay, but so this is why I said that I don't expect dynamics for the connection. And in the perturbative approach, we didn't find any free functions or any dynamics for the connection.
So you're not sure that it's not dynamical, but there are no indications that it is dynamical.
Exactly. Yes.
Okay. Because I was thinking about fermions. Also, fermions just have first derivatives in the equations, but they are dynamical.
Mm-hmm. That's
so
yeah.
I was puzzled by this statement.
Yeah,
So at the end, if gamma is not dynamical, at the end you get something different from a metric theory, or
yes.
or is it a metric theory at the end?
Well, in the end, the perturbative approach yields non-zero torsion. So it's not, it is more at the first order. It is like an Einstein-Cartan geometry. So you have metric and torsion. We don't have non-metricity. Non-metricity comes at second order or higher, not at this leading order. So we do have torsion.
Yeah, okay, but this, as far as I understand, does not mean that the theory is not metric. This means that you have some higher order terms at the end in the action, right? That the action is not just GR, but is GR plus some higher order terms. This is what I understand. Maybe I'm wrong.
Well, if you substitute the solution in the action, you will get new terms that depend on the metric and the scalar field. But I think it's just.
So what do you mean? What do you mean with metric theory? You mean just GR, just the Einstein?
No, something that only depends on the metric.
Yeah, we do have. This is the case because if you insert this back into the generic connection,
if you allow
connection is Levy-Civita plus essentially torsion plus non-metricity. And then you plug this back into the action, you get the Einstein-Hilbert term plus higher order terms, if I understand correctly. Maybe I'm wrong.
And higher order terms of what?
Of curvature of the metric and gradients of this theta and powers of theta.
No, I don't think. No, if you do it exactly, you don't get higher order terms of the.
And what do you get?
But you get the Riemann. You get Riemann squared, that is true, but contracted with the epsilon, so you don't really know what it looks like. So
you have the expression. So do you have the expression for the action once you have plugged the distortion back into the action? Because you have a solution for the non-metricity and the torsion. Do you have the expression for the action?
What you will get is when
this is the first. This is the initial. This is the initial action, right? Where,
this is the initial
where gamma is dynamical.
Yeah, but even in the exact case, if you split the connection in Levi-Civita plus torsion and non-metricity, then this term here, the Levi-Civita part is going to give the usual metric version of Chern-Simons theory. Okay, and then you will get all the other terms due to torsion, non-metricity, and different couplings among them.
But these are high order terms, no? Because you show that torsion is some function.
You also have couplings. Yes, you have couplings between torsion and metricity with the metric Riemann.
But torsion and non-metricity are functionals of the metric and theta once you have solved the equations, right? You showed me before.
I think so. Yes,
you showed me.
I would say yes. I would say yes.
So at the end, the theory is a metric theory because it's GR plus.
It's a metric representation. Yes.
Yeah. Okay. Okay.
Yes, in that sense, we agree. Yes.
Oh, okay. Okay. Thank you.
Okay, so next question by Philippe.
Yes. Hello there, Gonzalo. Thank you for the talk. I wanted to make a very small comment, which was not really about your talk. It was something you said at the beginning about Weyl gravity not having metricity. I mean, as formulated by Weyl, that's completely correct. However, if you replace d mu by d mu minus a mu, and you use that as the connection, and you plug that into the Dirac equation with a spin connection, the a mu term drops out identically. That's a mathematical fact. However, that means that it sounds like Weil's electromagnetism doesn't couple to a Dirac fermion, and that statement is actually true. However, you can save the theory by replacing d mu by d mu minus I a mu. But then when you plug it into the Dirac equation, you find that the Riemann side and the a mu side separate, and the Riemann side obeys metricity all over again. So actually, you can use Weil's approach and not lose metricity at the end. That's something I published a few years ago. It's just a comment. It doesn't change any of your results. It's just point. It's just point 3.
Thank you for the comments.
Okay, thank you. And Srava, do you have a question?
Gonzalo, thanks for the very nice talk. My question is about the action. So you basically have GR term and the point region with some scalar, right? So
yes.
So I'm wondering if suppose if you start with r plus r square plus this term, point region term, and how your results will change. Suppose you don't put any scalar there. I mean, r plus r square, just this Saint-Simons term. That's it.
Can you say that again? If I start with what? With the scalar coupled to what?
No. If you start with r plus r square, like Sharabinsky theory, plus the Saint-Simons term, well, if you do conformal transformation, you do see that the scalar field is coupled to the Saint-Simons. But I'm just wondering how your results will change.
So let me see if I get the point. So if instead of r, we had r plus r squared and then Saint-Simons.
Yes.
Okay, so in that case, there are not many changes. The difficulties are essentially the same because the Starobinsky part, you can solve it in the metric affine formulation using a metric which is conformal to G. So, and that conformal part absorbs the effects of the f of r part of the action. Okay, so all the difficulty lies in the Riemann contributions. So these difficulties are here in Chern-Simons theory, but even if you consider Gauss-Bonnet theory in a metric affine formulation, and you try to get the solution for the connection, you are going to have many, many problems. I mean, you can, in Gauss-Bonnet, you can verify that Levi-Civita is a solution, but we don't have a generic algorithm to obtain the solutions, to see if there are other solutions. This is not known. So the connection equations with Riemann elements in the action are really completely unexplored territory. So it's something completely unknown. So we have to use our imagination.
Okay. Thank you.
Okay. Thank you, Gonzalo, for again for your presentation.
My pleasure.
And now we can move to the last speaker of this session, Andrea Giusti.
Hi there.
Oh, hi, Andrea.
I'll try to share the screen.
Okay, great.
Okay. Is it full screen?
Yes, it's full screen.
So next.
And also to ask, do you want a reminder when you have 5 minutes left? Or
yeah, sure, that would be useful actually.
Okay,
thanks.
So I will give you a reminder. And Andrea will talk about thermodynamics of scalar tensor gravity. So yeah, feel free to start as soon as you're ready.
Okay, thank you very much. And first of all, let me thank the organizers of this such a nice event for inviting me. It is a pleasure to be here, at least virtually. And the idea behind this presentation is to introduce you to an alternative perspective on the connection between gravity and thermodynamics, specifically one that relies upon the effective fluid description of scalar tensor theories rather than on a thermodynamics description of the space-time itself, as it would happen, for instance, in the fundamental work of Jacobson on the thermodynamics of space-time. So let me start off by simply reviewing the general idea behind our approach. And in a nutshell, the idea is to start off from a general scalar tensor theory of gravity in the Jordan frame, which is given by a general Lagrangian like this one, for which we can actually compute some field equation by the standard variational methods, which ultimately will reduce to an effective Einstein field equation and an equation for the dynamics of the scalar field. Then, if we look at the effective Einstein field equation, we see that the right-hand side of this equation splits into two contributions, namely one that keeps track of the coupling between the matter content of the theory to gravity through an effective gravitational coupling, which is measured by the scalar field, the additional scalar field, and a second piece that keeps track of all the contribution due to the scalar field in this particular equation. Then the key idea is to try to interpret the second piece as an effective stress energy tensor for an effective fluid, for which we can compute some kinematic quantities, such as the shear tensor, the expansion scalar, and the rotation tensor. And then, looking at the constitutive equations for such a fluid, we should try to find a thermodynamic analogy for this set of theories of gravity. So this is basically the idea in a nutshell. So let me start by reviewing the effective fluid approach to scalar tensor gravity, which is a well-established approach to this sort of theories. And in particular, let me focus on the case of first generation quotation marks scalar tensor theories of gravity in the Jordan frame, which are defined by this very well-known action, for which omega is basically the Brans-Dicke coupling, and the effective gravitational coupling scales like 1 over the scalar field, which is supposed to be positive in order to guarantee an attractive gravitational interaction. Now, if we compute the variation of this action, we get the fields equation, which are very well known. And in the next step, I will basically focus on the effective Einstein field equation, which is the first one in this slide. Okay, if we look at this equation, we immediately recognize the Einstein tensor, of course. A second piece in the first piece in the right-hand side, which is basically the coupling, the gravitational coupling for matter, which is measured by the effective gravitational coupling, and a last piece, which collects all the information about the scalar field, which we want to try to interpret as an effective stress energy tensor for this phi fluid. And now the idea is to look at this piece and try to draw some connection between the properties of this effective fluid and some sort of constitutive relations for thermodynamics of irreversible processes. Okay, so let's start off by trying to characterize this effective fluid. And the natural way of doing that is by assuming, for instance, the scalar field to have a time-like gradient. In this case, we can use this time-like gradient as the basis for the definition of a four velocity of our fluid. And that basically allows us to define a time direction for a 3+1 splitting, from which we can infer the three-dimensional space associated to the commutating observer through the standard projection operator given here that satisfies some very well-known properties. But then now we can use these quantities to investigate the kinematic components, the kinematic features of this fluid. And first of all, the most important thing we have to compute is the velocity gradient that for this specific case is simply given by this expression in terms of the gradients and the double derivatives of our scalar fields. And the four acceleration for the fluid, which is again the covariant derivative along the four velocity of our four velocity, which is simply given by this expression here. And then lastly, we have to compute the double projection of the velocity gradient, which is known to split into three contributions, namely a symmetric trace-free tensor, which is known as the shear tensor, an expansion scalar, which is nothing but the trace of our velocity gradient, and a rotation tensor. Now, if we specialize this analysis to our specific theory, we immediately see that the expansion scalar is simply given by this expression here. The shear tensor simply reads like this, even though it's kind of cumbersome to look at. And lastly, we find that the rotation tensor vanishes, which basically means that our effective fluid is irrotational. Okay, but now let's go back for a second to the effective stress energy tensor for the phi fluid. And it turns out that if we look at this stress energy tensor, this tensor admits an imperfect fluid form. And basically, by using the projection operator and the force velocity, we can construct an effective energy density, heat flux density, isotropic pressure, bulk viscous pressure, and viscous stress tensor. And in particular, in the following, I will collect the non-viscous and viscous part of the pressure into a single quantity, which we will call simply the total pressure for convenience. But now, if we perform all the projections onto this stress energy tensor, we find this set of rather convoluted expressions for our effective quantities for the fluid representation of the theory, which are rather might look rather unremarkable unless we try to compare them with the kinematic quantities associated to our fluid. And specifically, if we do that, if we compare the imperfect fluid representation with the kinematic quantities associated to this fluid, we can actually see some similarities between, for instance, the force acceleration and the shear tensor with the heat flux density and the viscous stress tensor. And in particular, what we noticed, if you work out those details, even though it's kind of trivial, is that the heat flux density turns out to be proportional to the force velocity of the fluid, the force acceleration of the fluid, and the viscous stress tensor is proportional through the same function of the scalar field to the shear tensor for R5 fluid. And it turns out that these two equations resemble two of the constitutive relations of a very well-known approach in continuum mechanics, which is known as Eckart approach to the thermodynamics of irreversible processes. So let me briefly review the basic idea behind Eckart's first-order thermodynamics, which is a theory which is based on three constitutive relations. A relation between the bulk viscous pressure and the trace of the velocity gradient through the bulk viscosity, a generalized Fourier law, which also includes a contribution due to the inertia of heat, and lastly, a relationship between the viscous stress tensor, which is supposed to be proportional to the shear tensor through the so-called shear viscosity. And if we now compare the effective fluid representation and the kinematic quantities that we have found in the previous slides, and we recall these specific expressions for Eckart first-order thermodynamics, we can actually identify a precise notion for the bulk viscosity, the shear viscosity and a temperature, and the product between the thermal conductivity and the temperature for scalar tensor theories of gravity. And in particular, the first thing that one notices is that for our specific class of theories, the projection of the temperature gradient turns out to vanish all the time, and the temperature is conveniently always positive. Instead, the only weird effect that appears compared to the standard result in continuum mechanics and thermodynamics is that the shear viscosity for our classes of theories of gravity turns out to be always negative and equal to half the product between the thermal conductivity and the temperature. But then we can actually look at these two equations, namely these two expressions here, and try to provide one possible interpretation for this analogy by solving this couple of equations. And probably the simplest way to solve this system is by taking the temperature to be 1 over the scalar field, which basically means that the temperature is a measure of the effective gravitational coupling of the theory, which basically forces the thermal conductivity to be related to the norm, to keep track of the norm of the gradient of the scalar field. And this is just one of the possible interpretations that one can get by solving this couple of equations. And if we now look at the GR limit for scalar tensor gravity, which basically corresponds to setting the scalar field to a constant, we find that the temperature of our theory, which ultimately will be the temperature of general relativity, corresponds to the Newton's constant in this particular interpretation of the theory, whereas the thermal conductivity, again, within this interpretation, will vanish, which basically tells us that we can understand general relativity as a perfect insulator limit of this phi fluid. But then there is another perk of this particular thermodynamic analogy, which is given by the fact that we actually can infer an effective equation, and therefore an equation that governs the approach to equilibrium within this description, starting off from the constitutive relations and the field equations for our scalar tensor theory of gravity. And this looks substantially different from the one that appears in Eckart's very well-known work on first-order thermodynamics, but this is kind of okay since we have to keep track also of the dynamics of this additional scalar field. And of course, the physical interpretation of such an expression in gravity in particular turns out to be kind of complicated, though we can still consider a simplified scenario to gain some physical insights. And in particular, let's consider the case of electrovacuum with a constant Brans-Dicke coupling and a vanishing potential for the scalar field. This basically forces the field equation for the scalar field to become effectively the D'Alembert equation on curved background for our scalar field phi. Then, if the expansion scalar is less than 0, so is negative, the product between the thermal conductivity and the temperature will diverge at a finite time away from general relativity, which basically means that, for instance, near space-time singularities, deviation from of scalar tensor gravity from general relativity become extreme. At the same time, if we consider a positive expansion scalar, we have that in principle this term could dominate over this quadratic term, and therefore the theory would relax to general relativity over time. But this is actually a rather general comment, so let's try to look at some specific example to understand what happens within this thermodynamic analogy. And probably the simplest possible scenario we can consider is the case of scalar tensor black holes, for which we actually have a very general result, which was originally derived by Hawking for Brans-Dicke gravity, and then generalized by Faraoni and Soteriou later on for first generation scalar tensor theories. And the idea is that the theorem states that all asymptotically flat and stationary axially symmetric black holes in vacuum scalar tensor gravity will reduce to general relativity black holes, provided that the potential admits a minimum at which our scalar field can lodge on outside the event horizon, which basically means that if we look at the gravitational collapse to form a black hole in scalar tensor gravity, in the outer region, we will have that the scalar field will stabilize to this minimum of the potential, and therefore our product between the thermal conductivity and the temperature will stabilize to 0 outside the horizon. Whereas if we look inside the horizon, we have that the black hole will tend to, the temperature inside the horizon will tend to diverge as we approach the singularity. And therefore the singularity is the region inside the horizon will diverge from general relativity the closer we get to the singularity. Another simple example coming from, again, a specific class of a peculiar class of solution of scalar tensor theories relies on the so-called stealth solutions, which are basically solution of scalar tensor gravity for which we have that the geometry is given by a GR solution given a certain stress energy tensor, which was the one from which we started off our computation, plus a non-trivial scalar field, which basically means that we are in a situation where we have a GR solution generated by our matter content of the theory, on top of which we add a scalar field that does not gravitate. And an example of this scenario can be obtained, for instance, by considering the case of a vanishing Brans-Dicke coupling and a vanishing potential, and assuming an ansatz for the scalar field that is supposed to grow linearly with time. And this condition actually forces some restriction on the form of the stress energy tensor of the matter part of the action, which basically is supposed to only include electrovacuum scenarios, and also a condition on the vanishing of the trace of the stress energy tensor for the effective fluid. Furthermore, if we compute all the details on the kinematic side of this thermodynamic, of this effective fluid analogy, we immediately see that all kinematic components vanish, and therefore this basically tells us that Eckart's equations are identically satisfied within the specific class of solutions, which basically means that we can trust the definition of our bulk viscosity, shear viscosity, and product between the thermal conductivity and the temperature, which ultimately will be given by this simple expression for this specific case, which tells us something fairly obvious to some extent, namely the fact that the system will relax to general relativity at very large times, since after all, gravity is switched off at late times, since after all, the effective coupling in this theory will scale like 1 over the scalar field, namely 1 over the time as we take t to infinity. But okay, let's now focus on another class of examples, namely the ones that have some relevance for cosmology. And let's consider the case of a Friedmann-Lemaitre-Robertson-Walker universe. And therefore, we have to look at the case of an homogeneous and isotropic universe. This condition actually sets some strong constraints on the form of the stress energy tensor for the scalar field, which actually loses the contribution due to the heat flux density and the viscous stress tensor. And furthermore, this condition also entails some implication for the gradient of the scalar field and its norm. And ultimately, if we compute our fields equation for scalar tensor gravity in a FRW model, we immediately see that they reduce to the standard Friedmann equations for scalar tensor gravity, plus an equation for the dynamics of the scalar field. But then, okay, what happens to the kinematic part and the imperfect fluid representations that we discussed for a more general scenarios with a time-like gradient? Well, we immediately see that both the force acceleration and the shear tensor for our phi fluid will vanish, whereas the expansion scalar will simply be given by 3 times the Hubble parameter. Whereas if we look at the imperfect fluid, well, this will reduce to a perfect fluid, since the heat flux density and the viscous stress tensor will have to vanish because of homogeneity and isotropy. And therefore, we are left only with 2 contributions, namely the total pressure, which is given by this general expression here, and the effective effective energy density for the phi fluid. But now it is rather easy to split the contribution of the viscous and non-viscous part of the fluid, since after all, this piece here is the only one which is proportional to the expansion scalar. And therefore, the cosmological scenario simplifies a lot the splitting between the non-viscous part of the pressure and the viscous part, which will ultimately be given by these 2 expressions. But now, what happens if we compare the imperfect fluid representation, the now perfect fluid representation for the scalar field with the kinematic part, the kinematic analysis for the phi fluid? Well, we immediately see that the last 2 equations, namely the generalized Fourier law and the relationship between the viscous stress tensor and the shear tensor, will be identically satisfied, whereas the first equation will simply define our effective bulk viscosity. So, since these 2 equations are identically satisfied, we can carry along the same expressions for the other kinematic quantities that we have found in our previous analysis for the more general case. And instead, the bulk viscosity simplifies a lot and is simply given by this expression here, which is simply the rate between the viscous pressure and the expansion scalar. But then let's look at a specific example of solution in scalar tensor gravity. For instance, let's consider the case of the O'Hanlon and Tapper solution, which is basically a solution in vacuum Brans-Dicke gravity with a vanishing potential and some constraints on the Brans-Dicke coupling. Then the solution will ultimately be given in terms of the scalar field and the scale factor A, which will take a power law form, where the powers of these power laws are simply determined by the value of the Brans-Dicke coupling. And if we now compute the rate of change of our scalar field in time and our Hubble parameter, we immediately find all the expressions for our thermodynamic analogy for this solution, which immediately tell us that the solution will relax to general relativity as we take t to infinity. And furthermore, a nice property of this specific solution is that the rate between the viscous pressure and the non-viscous pressure is always constant. But then before wrapping up, let me just summarize a bit how to extend this whole analysis to the most general theory of scalar tensor gravity, having two or second order equations of motion. And in particular, let me start off with the subclass of Ordinsky gravity known as the surviving subclass or the luminal subclass, which is the one compatible with the luminal propagation of gravitational waves, and which is defined also by this very well-known Lagrangian. If we focus on this specific theory, we find that after all, the kinematic analysis carries out in the same way as in the first generation scalar tensor case, since after all, this analysis is theory independent. Whereas what is really theory dependent is the description of the effective stress energy tensor, which in this case, in the surviving subclass, still admits an imperfect fluid representation, and at the same time still admits a proportionality between the heat flux density and the Fourier acceleration for the phi fluid, and the proportionality also between the viscous stress tensor and the shear tensor through these more involved functions of both phi and the gradient of phi. But now, if we compare again these expressions with Eckert constitutive relations, we can again define our thermodynamic quantities associated to this analogy. And again, we find that the projection of the gradient of the temperature will vanish. And we find this more involved definition of temperature of Ordinsky gravity. Alternatively, if we solve again this couple of equations in the simplest way possible, namely the way that we have seen in one of the possible interpretations for the theory, we find that again the temperature will scale like 1/G4, which basically means that the temperature will scale like the effective gravitational coupling of the theory, and instead the thermal conductivity will keep track of the gradient, the norm of the gradient of the scalar field, and some additional functions which are known in Ordinsky gravity. Then, if we look at the expansion of this action onto a spatially flat and homogeneous isotropic background, we know that the dynamics of perturbation is actually governed by 4 parameters for this specific case, so for this specific expansion. And it turns out that our thermodynamic quantities T and K turn out to be actually related to some of these parameters. Namely, the temperature will be related to the effective Planck mass, as it was clear from the beginning, and the thermal conductivity will be related instead to the kinetic braiding of these perturbations. Lastly, what happens if we now consider the most general Ordinsky theory? So we include all the terms and all the dependency on the scalar field and its gradient. Well, it happens that the effective stress energy tensor for this more general theory will include a term which is proportional to the contraction of the Riemann tensor with the gradient of the scalar field, which in turn will break the proportionality between the viscous stress tensor and the shear tensor for the kinetic part of the theory, which basically means that the presence of these terms, which turn out also to be the ones that break the map to the Einstein frame for general Ordinsky theories, are the ones that break the analogy with Eckert first-order thermodynamics. And it is kind of nice to see that this analogy breaks down for those theories that somehow are not consistent with the luminal propagation of gravitational waves, even though there might be something more behind this, or might as well be a coincidence after all. So to wrap things up, the general idea was to use the effective fluid approach for scalar tensor gravity as a starting point, to draw a correspondence between the constitutive equation of our effective fluid and Eckert first-order thermodynamics. This analogy allows us to provide some definition of temperature, bulk viscosity, and shear viscosity for modified theories of gravity. And in particular, within one possible interpretation of this analogy, we have that GR can be understood as a perfect insulator limit of scalar tensor gravity. Now, the approach, besides that, we also have an equation that governs the approach to equilibrium starting from a certain configuration of the theory. And if we extend this analysis to Ordenski gravity, we find that only the luminous subclass of the theory carries out the analysis. Only the luminous subclass of the theory admits an analogy with Eckart first-order thermodynamics. And this is pretty much it. Thank you very much for your attention.
Thank you, Andrea, for this nice talk. Okay, there are a couple of questions. So the first one was Alexander Wickman.
Hi, Alex. Hi, Andrea. Great to see you. It's a very nice talk. Look, I have a question which you may suspect. So, formally speaking, that's a system described with an action, right, from what we started. And that means it's a conservative system. And if you have temperature and an imperfect fluid, then there should be entropy production. At least normal imperfect fluids are exactly like that. But here, I don't think you would have such like unique entropy production. Am I right?
I mean, in this context, you cannot really give a physical interpretation to the entropy associated to this fluid, because after all, it's not a real fluid. So you have some sort of entropy production, and you also have an additional fact, the fact that this fluid is not really isolated. Because it's interacting with gravity, and you cannot really provide a stress energy tensor representation of general relativity. So you cannot really see how this fluid interacts with the surroundings, which should be Einstein gravity.
Right. But still, in this interpretation, I would actually be more happy to see more alternative and more standard interpretation. Namely, if you have shift symmetry, then there is a conserved charge, and then there is the corresponding chemical potential, but no associated entropy, no temperature at all, because it's basically cold.
Yeah, the approach with the chemical potential is an alternative to that. That's right. Actually, I think I cited that at some point.
Yeah. I think so. But you see, the point is, I don't think from the point of view of purely dynamics, you can differentiate these two things, right?
Yeah, probably not. Yeah.
That's my problem. And partially related, if I may ask another thing, partially related question. So when you look at this, if you want conformally transformed kinetic gravity action, kinetic braiding action, which we used. So and do it in basically what you were considering is Jordan frame, but you could go equally to Einstein frame, right?
Yeah.
And then I think all your thermodynamical quantities would get changed. But then
that's right. Yeah, that could be right. Yeah.
That equation is like, formally speaking, things like entropy or temperatures, they are independent on filter definition, right?
Yeah.
So, but here I think they will all get changed.
Yeah, they will all get changed also because, they would be independent of field definition if they were physical, if they had some physical meaning. I don't really know whether the entropy defined here for this non-realistic fluid can actually have a physical interpretations like that.
Right. Okay. Because you see, formally speaking, for the shift, basically taking into account that it's a chemical potential, not temperature, this thing would not change. I mean, like you would know, okay, there is a conserved quantity, then there is basically a quantity which is associated to this conserved quantity.
Yeah, okay.
But the energy which you add if you increase number of charges.
But then I have a question. What happens since moving from the Jordan frame to the Einstein frame? You are basically losing the anisotropic part of the tensor, the stress energy tensor of the scalar field. How do you interpret the the viscous part and the heat flux density for your theory in that context?
In that case, there is no heat flux, and there is, but in our case, there is no heat flux per construction, because heat flux is the difference of energy carried orthogonally to your velocity, and chemical potential multiplied with the orthogonal part of the current.
Yeah, I see. Yeah.
So therefore, it's per definition in the series actually you will get 0. But of course, the viscous part goes away completely.
Exactly.
That's
yeah.
true.
Yeah.
That's
okay.
true.
So we are on the same line then.
Yeah. So basically, yeah, I'm asking because we spent like, I don't know, some good weeks trying to understand whether there is any preference we could.
And now I'm in the same process actually.
Good. By the way, maybe somebody else would like to ask as well.
Yeah.
So
Thanks, Alex.
Great to see you, man.
Yes, there is another question by Philip Manheim.
Yes.
Hi, Philip.
Andrea, thank you for the presentation. I have a small question and then a comment related to Alex's question a moment ago. Can you go right back to the definition of the fluid velocity?
Yeah.
Yes.
Right here.
That's the same definition as you use for the iconal velocity and the iconal approximation. And I wanted to ask you, that's all very nice, but what happens when you let phi be constant? What happens to the velocity in that case? Because that's the case you've been discussing.
I mean, at that point, you cannot really define a for velocity based on the scalar field. So basically, that for velocity will vanish as you take the limit.
Yes, but then you lose all the connection with the fluid.
Absolutely, yeah.
Yes, so in the limit in which phi is constant, you are not in a perfect fluid. You're just not in a fluid.
No, you are in a perfect fluid. You are in a...
No. Perfect fluid has a velocity. Rho plus P, you knew.
Yeah, okay, but the stress energy tensor is 0. So you can have whatever velocity you want at that point. This stress energy
I just don't see how you can construct that. Maybe there's a way to do it. I didn't see you constructing that.
It's trivial from here. If you take that limit for phi to be constant, the stress energy tensor becomes 0. And therefore, you can give whatever velocity you want to something which doesn't exist.
Yeah, but I don't think you can carry any of the thermodynamics over. And you see what does happen is in cosmology, you can use a constant phi. I saw you use a time-dependent one, which is fine, but you can use a constant phi and still get a Robertson-Walker cosmology.
Yeah, but
and you do have a fluid, and it does have a velocity. So there's something a little funny with the limit, but I mean, maybe you have a way to take it more carefully. Now, my second comment is I'm not really sure that you're doing thermodynamics at all, which is sort of what Alex was asking. Any tensor can be decomposed into a pressure, a density, a heat flow, and a viscosity. And it's got nothing to do with thermodynamics. It's just how T mu nu transforms.
Yeah, but the point is that
everything depends on this fluid velocity. Now, of course, if you do a phi field, you'll get those various components with some relations. If you do thermodynamics, you'll also get the same energy momentum tensor in general structure. But when you introduce the temperature is the Lagrange multiplier for the energy in the partition function. And I haven't seen any way that writing T equals phi.
Because I'm not doing that.
I know you're not doing that. That's why you shouldn't call it thermodynamics. That's why Alex is asking you what happened to the entropy.
And that's why I disagree with you, because actually I call it thermodynamics because it's as a form of correspondence between something that we know works in continuum mechanics, which is Eckart thermodynamics, and the constitutive equations of an effective fluid, period. So that's why I can call it thermodynamics. Then you cannot agree with, you might not agree with that. I'm fine with that, but I can call it as I please, provided that I specify what I'm considering.
Well,
this is semantics.
All I'm saying is
this is semantics. This is just
semantics. Any energy momentum tensor has 10 components, and they will all transform like thermodynamics, even though they may have nothing to do with
absolutely not, because they might not have any sort of connection with any known theories or constitutive relations that have any meaning in continuum mechanics. That's exactly
every known theory has an energy momentum tensor with 10 components.
Yeah, okay, so every known theory should have an equivalent known thermodynamics.
Well, that I would disagree with. But anyway, exactly, I understand what you've done. It's fine. I mean,
this is clear.
Yes. Okay.
maybe I could add something to what Philip was saying. In a sense, it's very important that the whole thing is actually floating, that there is some time-like vector internal to the theory. Because of course, if you take, let's say, a static configuration of a scalar field, then there is nothing floating there, and therefore it's not a flow of anything.
Exactly.
So in that sense, of course, we can always find, let's say, a fiducial observer and write it as if this is the fluid of basically the velocity of a fluid by specifying the local rest frame in this way. But this would be pointless because it's not an internal velocity. It's like, imagine you take electrodynamics and you consider a normal electromagnetic wave. Clearly nothing floating there because it's null, right? But of course, if I start using my, like if I'm an observer, if I'm a charge, then I could write it as if it is a kind of hydrodynamics. But it's not internal, it's external to the theory in a sense. So in that sense, you know, I kind of think it depends on, you know, this interpretation, if you want mechanical duality between, let's say, entropy, temperature, and chemical potential charge, things like that. But otherwise, okay, it's a fluid mechanics. That's true.
Okay. Are there any other questions? So if not, we are in perfect time, so we can thank Andrea again. Thank you.
Thank you all.
And now we should have a small break, 5 minutes, right? And then we come back for the discussion session. So yeah, see you all in 5 minutes. So 7 minutes past the hour. Yeah.
You can take a nap for 5 minutes. There was an earthquake here a while ago, 7.3.
Yeah, I was reading, like some people are texting me, but in Kyoto we could not hear it, but you cannot feel it, but you felt it. Yeah.
Close to Tokyo, actually, so it was quite strong. The building was oscillating. It was the strongest one I have experienced.
Was it long?
Yeah, it is long. I really saw that our building was just moving. Yeah, so the whole windows and there was a lot of sound. So in Sebastian, he came out and he was wondering what's happening.
See you in 2 minutes.
Yes, yes.
Okay, maybe we can start with the discussion session. So with all the speakers of the day. And yeah, I stopped Sravan before, so maybe we can start with the Sravan question for Alessia, and then yeah.
Okay, so I have my question to Alessia. Actually, I missed part of her talk, so I don't know if she discussed this. So the solutions she found, do they related to or come under some class of solutions which were found in for stellar gravity? In stellar papers, there are these three classes of solutions: 0, 0, 2, 2 whole, and 1, minus 1. And if I understand from the last part of the talk, so she was discussing the solutions for non-local theory, which 1 over box. I want to understand how the solutions are different, if they have some similarities with those found in stellar gravity.
So two different things. So the solutions studied by Stella, they asymptotically they behave differently. So because of the R-squared terms, asymptotically you also have the Yukawa type contributions, and this is not covered by our analysis, because we only have like inverse powers of the radial coordinate, and the expansion about r equal to 0 is another region. So it doesn't. That case is not really covered by our analysis.
Okay. Okay.
But in any case, just to clarify, it's not that we wanted to study solutions to 1 over box. That is the effective action that you must have if you insist on having black holes like Hayward, Bordin, Simpson, Visser, and so on.
Okay. Okay. And they have another comment actually. So there is a paper by Bob Holdom, so who has discussed extensively the solutions of higher derivative gravity. So basically he went up to 6th order gravity, and he concludes the following. So suppose if you find solutions using some Frobenius method or numerical methods, and then if you try to match those solutions with the linearized ones, you cannot always succeed, especially in the context of higher derivative gravity. So, and the conclusion he found that suppose if you take this criterion, if you go 6th order and beyond, the only solutions you will be left with are regular solutions. There won't be singular solutions. I don't know if you are aware of this paper. So I'm
yes,
curious
so
how. Yeah.
We discussed with Bob Oldham indeed, but our analysis is indeed consistent with his paper, because the first correction that he finds is of the type 1 over R26. And what we are saying is that if you have a local action, then the corresponding black hole solution will have corrections to the Schwarzschild term of the type 1 over R to n, with n bigger or equal than 6. So perfectly consistent. And yes, in that case, you also don't have a singularity anymore. So you don't really need this type of regular black holes or compact object. Of course, I mean, if they are realized in nature, that is another story. But in principle, if you go already at cubic order, it is true that you don't have singularities. But this was,
okay.
I think, yes, probably the paper was the first paper in this direction, yes.
So since you agree, your results agree with Bob Holdom's conclusion, so your solutions fall under 0-0 class, because his conclusion is 0-0 class of solutions remain and they are non-singular. So if you go 6th order and beyond, or even 4th order. I don't remember exactly, but 6th order for sure.
Yes, I think he was studying cubic action, and I mean, it is regular, okay, but in any case, our analysis is about asymptotics, so it is compatible with what he says.
Okay, thank you. If Ilya is there, I want to ask a question to him. He was asking a question to.
Before that, if Alex's question is related to the same topic, maybe we can, you can ask. Otherwise, yes, the same.
Let's try and go because I want to ask somewhat different.
Okay, okay.
Is there?
No, he's not here now.
Okay, then it's fine. So maybe Alexei, you can proceed.
Yeah, so maybe I will ask, I don't know, is Carlos Herrera, are you around? Somehow?
Yes, hi Alex.
Hello. Actually, well, but before I will ask you, I will just say something to everyone because from Luca, it was a request to me to put a link to YouTube channel, and now on the website next to the programs there is a link to YouTube channel where you can follow the talks which you somehow missed or maybe will miss, I don't know, or maybe in the future. So the link is there. So you just navigate to the website and it's there. And the question which I want to ask Carlos to you is the following. As I got from your talk, you are trying to mimic black holes, and for doing this, you are using scalar fields and you're using vector fields and you couple them to GR. My question is, have you considered not coupling to GR, but rather GR generalizations, or maybe GR generalization instead of matter fields? Because it is known that not every generalization can be expressed like effective matter. So it's not like, I mean, if it is f of r gravity, okay, then it is effectively scalar field. But if it is some combination of higher rank tensors, it's not obvious what it is at all, and it may be purely geometrical object, which may play good for what you are doing. The question is, have you tried this direction?
Okay, so thank you for your question, Alexei. So in my talk, I was focusing on these sort of objects called bosonic stars. So these are solitons. So they are different from black holes in the sense they do not have a horizon. They are horizonless. And well, we are not really trying to mimic black holes. We are trying to mimic some of the black hole phenomenology. In this case, well, there is an observable, which is a gravitational wave transient, which is interpreted as an event that has black holes as progenitors and a black hole as an end state. And we are saying, look, I mean, we have non-black hole objects, which are these bosonic stars as progenitors, and we have a final object, which is a black hole, and it can mimic the signal with what we know about the signal. And, you know, statistically speaking, one cannot really say that the black hole interpretation is preferred. So your question is, can I consider similar objects in more general setups? Well, the bosonic stars that I was talking about, they correspond to scalar or vector fields with a master minimally coupled to GR. In that case, I'm talking about GR, so we still have the strong equivalence principle and so on. But bosonic stars of similar type have been considered with non-minimal coupling. So you can have also scalar or vector fields non-minimally coupled to gravity with coupling, say, to the Ricci scalar or higher curvature invariance. There's some literature on this. So you can have this sort of object in more general setups. Of course, if you go to modified gravity, if you have higher curvature corrections, other models, the question about if you can have solitonic solutions is a question that is interesting. So in general relativity, I mean, it's a long question dating back from the early days. Einstein himself addressed it. So can you have a geon kind of thing? Actually, the terminology is from Wheeler. So you can imagine, could you have a bundle of gravitational waves that forms a solitonic object, a kind of compact object where the waves are kind of tied up by their own weight? So, and this has no horizon. And in general relativity, under some generic assumptions, you can show that it does not allow for a stationary such configuration. This is not clearly the case. Well, this is not always the case if you modify your gravity model. So you can have, perhaps even in some models, some purely geometrical configurations, which are kind of solitonic without the need of something that you interpret as a matter field. Of course, then if you go to something like f of r, you can map some of these theories into scalar tensor models, well, with some scalar field coupled to gravity. So in some cases, there could be a mapping. But a key ingredient in this sort of models is really that the field is complex and it has a mass. The mass provides the trapping mechanism. You see, you have an oscillation. Why is this thing not collapsing and forming a black hole? Because it has some pressure. And the pressure is due to these oscillations. And these oscillations, though, they must be bound. So there's a potential barrier at infinity so that the energy, the frequency of these oscillations is below this potential barrier. So you really need the mass. The mass is fundamental. So if you don't have the mass, that is the mass of the scalar field, you don't have a similar configuration. And the complexity allows you to have really stationary or even static solutions in the sense of your metric being static. So you can have something analog for real fields. They are called oscillatons. So in that case, you also have a frequency, and it's a real field. So you don't have this trick of making your scalar field or your Broca field e to the minus I omega t, which then, because you're multiplying phi by phi star, it cancels out. And therefore you get something at the level of the energy momentum tensor, which is time independent. So if you have a real thing, you can have something like a cosine of omega t. But then the non-linearities, because of the coupling to gravity, create higher harmonics. So it's not something that is completely time independent. So, and actually these objects called oscillatons, they leak slightly. That is because you have still the potential barrier, the frequency, the basic frequency is below it. But then because of these higher harmonics, which are produced due to the nonlinearity of the theory, there is some kind of leaking of this object. So there are some solutions people have computed. They can be rather long-lived. So that depending on the mass that you choose, you could have them with a lifetime, which is longer than the Hubble scale. And people consider them as well. They are more complicated technically, but, and they are not strictly speaking static in terms, well, the spherical ones or stationary, the rotating ones. Actually, no one has computed the rotating ones. It's a technical problem, which is complicated. So, yeah, I think that the message of my talk is a little bit that some phenomenology you could mimic with some objects which are not black holes. That's kind of interesting, which is a word of caution, because in the case of gravitational waves, we are interpreting these signals given a paradigm. And actually, we do not have many alternatives in order to do this comparison, because one of the things is that in alternative models, being modified gravity or just exotic compact objects, there are no libraries of these waveforms that you can compare against the data. And it's a difficult problem. It's a technically difficult problem. And some of these models might be actually impossible. For instance, recently people have been analyzing some models which are these extended scalar tensor theories, in which you have a scalar field coupled to the Gauss-Bonnet. So the Gauss-Bonnet is a nice combination for the reasons that you know of. Yeah, and people have computed black holes in these models. There's some spontaneous scalarization type of phenomena. And people have done some evolutions, like Pretorius and his group. And what they find is that although it seems a very nice model on the paper, the evolution stops being hyperbolic. So the equations become elliptic in some, given some initial conditions in the future. So, you know, some of the good properties that we have in general relativity as a Cauchy problem, as an initial value problem, are not guaranteed in modified gravity in general. And that is a very important point. Of course, it's a difficult point, and I'm not saying that one has to tackle it immediately as one is considered modified gravity, but it is an important point. And the advantage of these models that we've been considering is that this is just GR, and you put there some matter content, which is fairly simple and fairly under control. Nice. And still you can have some non-triviality and very interesting objects. So, yeah.
I see. Okay, thank you.
Thank you for your question. Thank you.
Okay.
Even in the scalar tensor, you still have to choose the initial conditions to understand these bosonic stars, right? I mean, you certainly choose some kind of initial conditions. I mean, it should be the problem seem the same even in the modified gravity, right? I just want to understand your last comment.
Right. So what I'm saying is that the equations of motion, well, we know in general relativity, well, in vacuum, and now depending on the type of matter as well, that the initial value problem, the Cauchy problem, is well posed. So the equations remain hyperbolic during the evolution. That's what it means. And if you just put as your matter, you know, a Klein-Gordon equation with the usual D'Alembertian operator, this is assured unless you could put some pathological part there, like, well, n negative energies, things violating energy conditions. But in general, in modified gravity, this is something that has to be assessed. If I just give you any type of action, this is not guaranteed. So you do not know if there is some sort of hyperbolicity in the evolution, which is fundamental in order to have a well-posed initial value problem. So what I'm saying here is that even in this simple setup, there are opportunities. And here we have, you know, the technicalities more or less under control. Because, you see, it took a long time for people to be able to do the two-body problem in general relativity, you know, and only around 2005, people managed to do, you know, binary black hole evolutions and get to the merger. And it took a long time. It took a long kind of understanding of the subtleties of the problem. And there was an infrastructure that was built for the purpose. And we can use that in new models, as long as the new models are not so different from the model for which this was understood, meaning you can use it for general relativity with some matter. People use it for neutron stars as well. But if you try to deviate a lot from your original model, then you'll have to rethink a lot of the things in this infrastructure. So, for instance, to get these waveforms, you do have to make these collisions. So the initial data there, you have to put your boson stars, which you've computed. Even that is an issue, because if you want to evolve just a single boson star, you just need to know the solution. But if you want to put two of them, then you'll have to actually solve the Hamiltonian and the momentum constraint for that sort of configuration. And well, one thing that we do to get away with it is just to kind of separate them enough and superimpose the solutions. And then the violations of this Hamiltonian and momentum constraint can be under control. It's not a true solution, but then the evolution actually kind of flows into the solution. But for instance, if you want to make a binary, and if you, well, in my talk, I was telling you that I was doing these head-on collisions. If you want to make an orbital binary, then you really have to give velocity. And then you have to address the problem of the initial data, meaning to solve the Hamiltonian and momentum constraints, which becomes a little problem in itself. So yeah, well, that's what I would like to say.
Okay, thank you.
Thank you.
And motivated by this, I have a question to actually Gonzalo Olmo. So Gonzalo is here.
Yes, I'm here.
Yeah, so I'm curious, as Carlos mentioned about the difficulties with modified gravities, and I'm wondering, in metric affine theories, you basically increase the number of degrees of freedom. Are there any solutions in the like compact object or ultra compact or horizontal-less objects in the metric affine theories? I don't know about this. Maybe you have some idea.
Yes, well, you increase the number of degrees of freedom formally. So in principle, you allow the connection to be independent, but in the end, when you solve the equations, depending on the model, you may end up having the same number of degrees of freedom as in general relativity. Okay, this is what happens in any theory that is constructed with the Ricci tensor, not just the Ricci scalar. Also, if you include Ricci, those theories typically the connection can be solved in general, and you get something that has the same number of degrees of freedom as GR. Okay, and then regarding the solution of compact objects in these theories, you have different types. So the simplest solutions are of the black hole type. So black holes with electric charge or with, typically electric fields, electrodynamics. But you can also find solutions for boson stars. Okay, actually, we have a paper from last year where we used some correspondence. There is a correspondence between the equations of this type of theories based on the Ricci tensor. You can always rewrite them as the equations of motion of general relativity. Okay, and that's a clear advantage to use numerical methods. Okay, anything you can do in GR numerically, essentially, can be done in these metric affine theories of gravity based on the Ricci tensor because of this correspondence. And so far, we have applied the method to boson stars.
Okay. I have another small question. So I was reading some metric affine theories which kind of offer some geometric dark matter, like some vector field which is comes from the connection. So it's not basically the particle like, but it comes from geometrical modification, like higher curvature terms. So I don't know if people have found black hole type solutions in those kind of theories. Are you aware of them?
I don't really know.
Okay. Thank you.
Okay. Yeah, Philip.
It's not a question. Alexei said a moment ago that you had a YouTube channel going. I've got two issues. One is if you want to record anyone, I think you have to have their permission first. And the second is this YouTube channel, is it just internal to the conference or is it available to any one of the billion people that look at YouTube? And I don't think you should have done that without asking us first. That's all.
I believe Luca was asking before sessions.
Oh, okay. So that was for the speakers.
Yes.
But not for the discussion.
If you mind, the discussion is there, it can be cut.
Well, I don't mind. I'm fine with it, but I think it's, I think if you're going to do that, you have to make
speakers were requested, and technically, yes, it is publicly available.
Okay, all right. Well, it will be very useful for me because the first talks in the morning are going out at 5:30 my time, and so I have to miss a lot of the morning session. At least if it's
actually on the first day we asked, so we record. But if any problem, speakers can tell. So
I don't mind. That's okay.
Yeah. Okay.
Okay. So I don't see any hands raised. So maybe I will ask a quick question to Alessia. It's just about the fact that is it justified that we do not include matter in the effective action? Like you're already looking at vacuum solution, right? So I wonder, maybe, I don't know, as you said, the Howard geometry, and I think also the Simpson-Visser, they actually, you can write them from a variation principle if you have Ricci scalar and nonlinear electrodynamics. And it's true that the matter action in that case is very strange and not a very realistic, I mean, I don't expect this to be a realistic matter field. But I don't know if you have a higher order term for the gravity sector and a realistic stress energy tensor, if you can get them. I cannot hear you, Alessia.
Now?
Yes.
Okay, great. So I was saying this is a really good question, and we have been thinking about it because, so in principle, what one can do is to set up the path integral as a sum over all quantum gravitational fluctuations and also over matter fields. And the result then it will be an effective action that depends on your effective degrees of freedom, so the metric and the additional matter fields. But then at that point you can further integrate them out, and then you are left with an effective action that depends on the metric only. So our guess is that the action, an action that is something like Einstein-Hilbert plus something like nonlinear electrodynamics can be mapped in a non-local gravitational effective action with this type of 1/box operators. And in this case, I mean, this would make sense. And so the point would be that if you have something like nonlinear electrodynamics, at the level of the gravitational dynamics, it would be the same as having infrared non-localities at large distances. Now, of course, certain metrics like Hayward, Pardin, and Simpson-Visser can be modified slightly to be compatible, for instance, with an action principle coming from a local action. This is absolutely possible. So the only point of our work is just that one has to be careful even with the compatibility with the asymptotic, so with the GR, if you want.
Thanks. Yes, thank you. Okay, Zravan, you have another question, or is this still?
I have a question to Andrea, and also maybe also Wickman, if he wants to comment about it. So I have a question basically about Hordensky theories, which is
probably I'm the wrong person to ask then.
Okay, so I have the following trouble with the Hordensky theory. So it is the most general scalar tensor theories people have studied extensively, but from fundamental point of view, from quantum gravity point of view, why this most general theory is needed? Because it has so many functions. It's not. Or is there any possibility to fix them from fundamental point of view?
I mean,
or it is just
I have the same question.
Curiosity, because we can write a most general action. This is my first question.
I mean, I have exactly the same question. Why do we really need it? Actually, I took some interest in Hordensky gravity only from a mathematical perspective, just to find this analogy. And just because it was the most general theory you can write with second order equations of motion. That's the only thing that I was interested in. On the physical side, I agree with your points, actually.
Okay.
Well, I don't think it's, you see, the point is, it's very hard to motivate. For me, my motivation was in actually kind of hydrodynamics, because I don't think it's something fundamental. I think it's just some effective degree of freedom.
Exactly.
It's some weird dynamics of God knows what and some limit. It's probably also applicable for the whole Hordensky story. On the other hand, normal general relativity is not renormalizable. It's not polynomial. And actually, it also has higher derivatives entering just linearly there, right? Mm-hmm. So in that sense, there's some structural similarity with this scalar part in Hrudensky. So at the end, okay, it's mathematically interesting that this can exist.
Yeah, I mean, but there is no fundamental justification, I would say.
But you see, it's a very interesting question whether there should be a fundamental verification for anything, because formally speaking, you can always, if you believe in effective field theory's approach, right? It's just effective field theory on one layer and then effective field theory on another layer. In most cases, you even cannot derive one from another.
Yeah, that's right.
Because who can derive, I don't know, superconductivity from QCD and QED?
That's right. Yeah.
I don't think it's possible, right?
Field theory is fine, but what I do not find is any reason, any physical reason, except the mathematical construction for Hrudensky theory. So I mean, that has been the question. I'm trying to find an answer, some kind of motivation.
No, motivation, you see, if you buy the story a la hydrodynamics, right, of some, let's say, some condensate, right? So for me, I like to think that this whole thing is very cold, no entropy practically. In that case, sure, you can say what is encoded in these functions. For example, in the first function, so K of x or P of x, it's equation of state of the superfluid. Then this function G in front of box phi, so G of x, this is exactly how your transport coefficient works. How does it depend basically on chemical potential? If you look at real systems, these functions are completely horrible usually. They're very complicated.
Yeah, but again, this works only for a subset of Hrudensky, not for the whole thing, right?
Sure. But you see, the point is we don't know. It's that's an interesting story, because if you talk to people who do hydrodynamics, they like to derive also operators which include non-minimal couplings.
That's true, yeah.
That's surprising, but it is true. Then the question is, okay, whether the non-minimal couplings they would like to consider have anything to do with the non-minimal couplings from Hrudensky, but I wouldn't be surprised if it can be there. The question is for what kind of superfluid, what it is. Okay, that's we don't know.
Yeah,
clearly. But you see, of course, if you want to have some more fundamental physics, like maybe we would buy some beauty there. I don't know. Is the whole thing is, let's say, conformally invariant or well invariant? Or I don't know, this scale invariant maybe. But there, for example, for the kinetic gravity braiding one, so the simplest cases, you could write actually scale invariant Lagrangians, as it's done by Rubakov. Well, the question is whether this verifies much, that's we don't know.
Yeah.
Also, there are statements about their renormalizability, or basically that the quantum corrections to these terms are not necessarily that big. Also, there's some subclass which could be Galilean invariant.
Yeah, that's right. Yeah.
That's also interesting in flat space time. So I don't know. It just depends on your attitude.
Yeah.
But if I can comment on that, can you hear me?
Yes.
Yeah, sure.
Right. Yes. So regarding the question of effective field theory versus fundamentality, so of course we would not be able to test a complete theory to arbitrarily large scales, but this is also not the point. I think the point of having something fundamental is that you don't have infinitely many parameters to tune. You have only a few, and then you can predict all the rest. So this is the key point of that makes the difference between having something fundamental and having something like an effective field theory. So fundamentality, I would still say that it is important to the extent that we can, of course, investigate.
Yeah, but you see, in hydrodynamics, it's whole equation of state, and the equation of state is a function.
Yeah.
And if you look like in realistic examples of what these equations of state are, it's a horrible function. It's really not a nice one. And also, like it doesn't look like an expansion in, let's say, kinetic term at all. It's not power law expansion. It actually has non-analytic parts. You know, when people study now all this positivity bounds, all this stuff. If you look at simplest examples of fluids, of course, fluid should not be analytic when the whole thing goes to zero, right?
Yeah.
I mean, for example, you take chemical potential in this description, right? And you drive it towards zero. And naive effective field theory expansion is like in this basically chemical potential squared. But if you look at normal systems, the whole description breaks down, because zero chemical potential in many cases would mean that there is also zero charge. Zero charge means that what kind of hydrodynamics can you have if you don't have particles? If you have one particle per universe, it's not hydrodynamics, it's probably some kinetic theory which you want to do. And you know, in most cases, these things don't have normal Lorentz invariant state. If you approach closer to vacuum, to Lorentz invariant vacuum, it's not analytic. There are some structures with square roots and logs of square roots and God knows what. So it's, I don't know. On one hand,
from point of view, I really like this way. So it's indeed complicated. It's very hard to mimic any simple stuff. So, but my question is actually in line with what Alessia said. So we have these functions, a lot of unknown functions. What is the best way to fix them? So, I mean, whatever the physics we do, whether it is cosmology or black holes, well, in cosmology, there are already some constraints on the Howard density theories, and well, already the speed of gravitational waves kills a lot of these terms, but still we kind of apply in the context where these constraints may not be applicable, but it's fine. So maybe there may be some principle we can try to fix these functions, at least the form of these functions, to reduce the parameter space. Exactly what. Yeah.
So in the context of quantum field theory, you have a recipe to do so. And I'm not. I'm not the best expert in this, but next to me there are two, like Benjamin and Chris. So you can really set up renormalization group calculations. That what does that is to perform the path integral cell by cell, and then you compute the flow of functions of box as a function of the renormalization group scale. And this gives you, so if you study the flow of this and you are good enough to process the calculations and study the full RG flow, you have two information. One, what is the fixed point action that roughly corresponds to the bare action, your fundamental action of your theory, and this is a prediction. Okay. And the second, in the limit where all the fluctuations are integrated out, you have a clear prediction for these form factors. The point is just that it is extremely involved. So to do so, for which it will still take some time to have approximations to these form factors. Say even at quadratic order in a further expansion of the effective action.
Oh, I think when Sravan said that it would be interesting to look at what fixes this function, I think we should first start then from potential for, let's say, even Higgs. We don't know how does it look like in reality. Of course, we have like zero order approximation, which is polynomial, but then if you really include renormalization group flow, even if you know, like basically a standard model stuff, it has very complicated form. I mean, like if you really look for potential for an expectation value, it's a disaster. And it's not polynomial, it just has this complicated shape with logs and God knows what. And imagine it's like one Higgs and standard model. Imagine we have tons of other degrees of freedom. That would be much more complicated.
But in principle, you can study the flow of functions of a field.
Sure. Of course, in principle, it can be done, but in practice, I don't know.
In some approximation, this has been done for scalar theories. So in local potential approximations, that is the simplest one, but also going like in a derivative expansion up to 6th order, if I remember correctly. 6th order, yes.
Sure, but that's assuming that you know whole UV, right?
Sorry?
It's under the assumption that you know whole UV.
No, you essentially parameterize your action, and then you study the flow, and then the UV comes as a prediction in the sense that it is the fixed point, the UV fixed point of the flow.
No, sure, but in reality, you see, that's exactly the thing what I never understood. In reality, from UV, you can derive IR. From IR, you can never derive UV because you don't know what is there. And it's in a sense, randomization group is not a group, it's semi-group. It has one direction. Because by integrating out, you are losing information. If you cannot integrate in if you don't know what to integrate in. So that's the thing.
You can translate that, so you see, you think it is a semi-group because you start from a formulation in terms of an integral, the path integral, but you can translate that in a renormalization group equations. So they are differential equations, and once you have initial conditions for the flow, you can go back and forth. So that is not that is really at the core of the Wilsonian renormalization.
But you see, the point is you still need to know what are your fields in UV, how many of them are there, and each of them and how they're distributed and whatever, they will definitely change the picture. If you don't know the measure in your path integral, you cannot do the job. You can only say, okay, I integrated out the whole thing in UV, I don't care. I now integrate only this portion in the say energies. Then yes, but otherwise you cannot make this assumption because you don't even know what is there. Imagine you start from, let's say, just normal superconductivity. It's a field theory, low energy field theory. But clearly, if you start doing like kind of quantum corrections and all these loops orders and then see how the couplings are running, you will never derive QCD. It's impossible. You definitely will not find gluons there. That's for sure. You will not find even atoms, I think, if you do it, because fundamentally your assumption, which drove you for this effective field theory, you started from normal atoms, from lattice.
Once you know symmetry and field content, you can analyze things.
Yeah, but the point is exactly that the content may change when you go between different energies.
Exactly. Exactly.
That's what Alexander is pointing to. That you see, you can start with, let's say, only mesons, and then you will not know that they are gluons. I mean, only working with mesons, you will not see that there's anything like gluons and quarks. That's the point. You have to have additional input that maybe you have to change the exophilium. So like he was saying, if you want to derive superconductivity, you cannot derive it just from the fundamental theory of quarks and gluons.
But that's all fine. But I mean, if you start with a theory of mesons only, you will not find a UV fixed point. So you know that this cannot be a fundamental theory. No, please let me finish. But if you start with QCD in the UV, we know that QCD has gluons in the UV, and you integrate it down, you can introduce like composite operators in a dynamic way in the RG flow, and then you have both gluons in the UV and the hadrons or mesons in the IR, and it's completely consistent.
They look like they are not truly there. Because if you, for example, study condensed matter systems, then you know that what happens beyond the critical point is that it's not obtainable in an RG flow because RG flow stops them. But you know, in condensed matter, you can have the field before and after.
No, but that's what I'm saying. You can use dynamic Bose-ionization, for example, for fermionic system, and you can completely treat it at all scales.
But they are not exactly the same exophilium as we call normally chiral perturbation theory.
Of course, they are related. I mean, in the UV, one set of degrees of freedom is important. In the IR, another set of degrees of freedom is important.
By the way, may I ask you something? What I don't understand. So, to my mind, if we do effective field theory, then we actually parameterize our ignorance, right? But ignorance implies that this is some universal behavior which does not depend on UV. So therefore, how can we then take the machinery which is created to ignore UV and then get information about UV. It's just impossible, right?
Theory and effective action are two different things.
Yes.
Completely
different. Sure, exactly. No, that's I completely agree. Sure, if you completely fix the meta content in your basically what are the fields with what you're working on, your degrees of freedom, then clearly, of course, you can just go and derive at whatever level of energies your effective action. Sure, that's no doubt. But you need to know the whole UV. Otherwise, if you don't know that, then imagine you go now past, you see, otherwise from our standard model, we could do renormalization group flow and discover, I don't know, everything what was behind there. But I doubt it's possible, right?
But the point is the RG will tell you if you can, if you have the full UV or not, if you could have the full UV or not. If you see that the RG drives you to infinity, then this is not a fundamental theory, it's an effective field theory. But if you see a fixed point in the UV, you have a chance that you got everything right.
Sure. With that, of course. With that approach, I completely agree. If you really see that somehow your RG flow approaches to UV fixed point, okay, that sounds at least as there is a hope that this is a kind of proper, that maybe you don't need any more degrees of freedom.
Exactly.
That's for sure, of course. That's definitely the case. However, you would never know whether, you don't need them from theoretical perspective, but you would never know whether you need them from observational perspective. So,
of course. I mean, of course, there's always the possibility of adding more and still having a fixed point, essentially IR physics, but then you have Occam's razor, essentially. If you get the same IR physics up to things that you cannot measure or that we cannot measure right now, then the simplest theory is the best theory.
Sure. No, of course. Look, this is clear. The less parameters, the better it is, right? But the question is whether we will be able to test it. Because also Razor is also saying that it's all basically pointless because then there is one unified explanation for the solids, it's God. So if we continue really this phrase of awesome Razor.
That's not true, because then you cannot make any predictions.
Exactly. That's exactly.
But you need some predictivity. Given some predictivity, you want to minimize the assumptions.
Yes. Of course, I was semi-joking. God is not about what we need to study.
One small question, Alex. So you said about equation of state, complicated equation of state in the hydrodynamics systems. So, well, in cosmology or black hole physics, where do we need complicated equation of state? At least observationally, we don't have any indications that we do require some complicated equation of state. Am I correct?
Well, observationally, look, we don't need it. But if you really look at, let's say, hot plasma, and in different regimes, it can be exactly if W equal 1/3, and we can deviate from it. When the things cool down, transit, whatever, it can be a complicated equation of state. What we can do, take even very simple thing, take relativistic fermions with given chemical potential, but without temperature. So zero, like extremely cold. It's an exercise in Landau issues, but we have taken this exercise and studied it in our paper. And then suddenly you see equation of state, which is bizarre. And it's like physical system, these fermions without any other interaction. I think it's actually called Fermi liquid, It's kind of, in reality, it's Fermi liquid. But okay, it's horrible equation of state. And what can be easier? Like it's the stuff without any interaction. And if you start introducing interactions, that would be like a disaster. And in most cases, we don't even know how to derive it. As you know, in most cases, these equations of state are derived in approximation of small interaction. And if the whole thing interacts, it's just some fitting functions what people use or whatever, some other stuff. So that's a problem, I think. And the same thing by the way, for transport coefficients. There's no really good basically way to say what it is. Except of maybe some symmetry considerations, something simple. But in most cases, people don't know. Like imagine, for example, in like normal aerodynamics, right? There is this Chaplygin gas. And it's bizarre, right? Because it's 1 over density in the equation of state. And we are talking about bloody aerodynamics, stuff which is flying.
Yeah, but the Chaplygin gas models are, at least in the, as far as I know, in the context of early universe cosmology, are widely applied. But well, I don't know how much they are useful to describe.
But you see, that's a different story in cosmology. I mean, like real Chaplygin gas from, Chaplygin didn't know about cosmology, I presume, at all. He only knew about aerodynamics, and that's what he cared about. And there's this type of equations of state, okay, appearing, which are relevant for whatever, some flows. I'm not a specialist in that, but, if such complicated equations of state can happen in our atmosphere, why cannot it happen in the early universe? It can be happening much more complicated things, I would say.
Okay, yeah, at this point of view, I understand, I like it, so, okay, thanks.
Oh, you're welcome.
I don't see any other questions, so maybe we can close the session. Maybe the organizers have some announcement or anything. I don't know.
No, I think we can just thank all the speakers today, especially our chairman, who is in Japan now and it's very late. So let's clap for